Hi, welcome to Beginning C++ Game Programming Part 2 by John Horton, a video course by Pact Publishing. My name is Doug Stevens, and I'm going to be the voiceover artist for this course. John Horton is a coding and gaming enthusiast based in the UK. He has a passion for writing apps, games, books, and blog articles about programming, especially for beginners. He is the founder of Game Code School, which is dedicated to helping complete beginners start coding using the language and platform that are best for them. He has authored many technology books, most recently these. This course is about learning C++ programming the fun way. In the first part, we learn the basics of C++, such as variables and loops. In this part, we would go through to advanced topics such as inheritance and polymorphism. Everything you learn will be put into practice by building a fully playable game. This is our final project. Thomas was late. Quite similar to the popular game Thomas Was Alone, our game will have fewer puzzles, but will also make the players race against the clock. Let's now see what we've got in store for this course. The first section of this course introduces the final project, Thomas Was Late, including the gameplay features and project assets. Then we would see coding the Thomas Was Late game engine, and also implementing split-screen functionality. Section 2 would have building an abstract playable character class, putting inheritance to work with the Thomas and Bob classes, and adding Thomas and Bob to the game project. In the third section, we'll code a polymorphic function to handle the collision detection for both Bob and Thomas. Fourth section would show building a Sound Manager class, building a HUD class, and using the HUD class. The last section would have building a particle system and using shaders in the Thomas Was Late game. I would like to inform you the prerequisites for this course. They're the same as Beginning C++ Part 1. Take a good look and ensure that you have them before you start coding. All the software used in this course is free. Obtaining and installing the software is covered step by step within this course. It uses Visual Studio for Windows throughout, but experienced Linux and Mac users will probably have no trouble running the code and following the instructions using their favorite programming environment. This course is perfect for you if you want to learn to build games or just use games as an engaging way to learn C++, or even if you just want to have loads of fun and impress friends with your creations. We'll learn C++ in a fun way. So, let's begin this journey together, and I hope to see a proficient C++ game developer in you at the end of this course. Hi, and welcome to the first section of this course, Abstraction and Code Management, Making Better Use of OOP. In this section, we will start off with an introduction to the final project, Thomas Was Late. We would then move on to structuring the Thomas Was Late code. In the later videos, we would learn building the game engine and coding the main function. Now, we move on to the first video of this section, the Thomas Was Late game. In this video, we're going to take a look at features of Thomas Was Late, creating a project from template and the project assets. At this point, if you haven't already, I would suggest you go and watch a video of Thomas Was Alone at store.streampowered.com. Notice the really simple but aesthetically excellent graphics. The video also shows a variety of gameplay challenges, such as using the character's different attributes, height, jump, power, and so on. To keep our game simple, without losing the challenge, we will have fewer puzzle features than Thomas Was Alone, but we'll have the additional challenge of creating the need for two players to play cooperatively. Just to make sure the game is not too easy, we will also make the players race against the clock. Hence the name of our game is Thomas Was Late. Our game will not be nearly as advanced as the masterpiece that we're attempting to emulate, but it will have a good selection of exciting gameplay features like these. A clock that countdowns from a time appropriate to the challenge of the level. Fire pits that emit a roar relative to the position of the player and respawn the player at the start if they fall in. Water pits have the same effect, but without the directional sound effects. Cooperative gameplay. Both the players will have to get their characters to the goal within the allotted time. They will frequently need to work together. For example, the shorter, lower-jumping Bob will need to stand on his friend Thomas's head. The player will have the option of switching between full and split screen, so he can attempt to control both characters himself. Each level will be designed in and loaded from a text file. This will make it really easy to design varied and numerous levels. Take a look at this image of our game to see some of the features in action and the components, assets that make up the game. Let's take a look at each of those features. The image shows a simple HUD that details the level number and the number of seconds remaining until the players fail and have to restart the level. You can also clearly see the split screen co-op in action. Remember that this is optional. A single player can take on the game full screen while switching the camera focus between Thomas and Bob. It is not very clear in this image, but when a character dies, he will explode in a starburst firework-like particle effect. The water and fire tiles can be strategically placed to make the level fun and force cooperation between the characters. Notice Thomas and Bob. Not only are they different in heights, but they also have significantly different jumping abilities. This means that Bob is dependent upon Thomas for big jumps, and levels can be designed to force Thomas to take a route that avoids him banging his head. In addition, the fire tiles will emit a roaring sound. These will be relative to the position of Thomas. Not only will they be directional and come from either the left or right speaker, they will also get louder and quieter as Thomas moves closer or further away from the source. Here, Thomas and Bob arriving at a fire pit that Bob has no chance of jumping over without help. This instance shows Bob and Thomas collaborating to clear a precarious jump. Here we see how we can design puzzles where a leap of faith is required in order to reach the goal. Look at this instance. See how we can design oppressive cave systems of almost any size. We can also devise levels where Bob and Thomas are forced to split up and go different routes. Creating the Thomas Was Late project is the same as the other two projects. I'll guide you through the steps in Visual Studio. First, you have to select File in the main menu, and in that, you have to click New Project. Now, make sure that Visual C++ is selected in the left-hand menu, and then select Hello SFML from the list of presented options. In the Name field, type TWL in uppercase, and also ensure that the Create Directory for Solution option is checked. Now, click OK. Now that our project is created successfully, we need to copy the sfml.dll files, which reside in sfml bin subfolder, into the main project directory. These are the DLL files we have to copy. My main project directory lies in Documents, Visual Studio Stuff, Projects, TWL, TWL subfolder. Let's copy them into the TWL subfolder. So, the project is now set up and ready to go. The assets in this project are even more numerous and diverse than the Zombie Arena game. As usual, the assets include a font for the writing on the screen, sound effects for different actions such as jumping, reaching the goal, or the distant roar of fire, and of course, graphics for Thomas and Bob, as well as a sprite sheet for all the background tiles. All the assets required for the game are included in the download bundle. They can be found in Section 1 Graphics folder and Sound folders respectively. As you can see, in Section 1 Graphics folder, we have images for background, Bob and Thomas, and this is our tile sheet that we're going to use for all of our background tiles. This is the Sound folder, where we have various sounds which are Fall in Fire, Fall in Water, Fire 1, Jump, and Reach Goal. Now, in the Fonts folder, the font that is required has not been supplied. This is because I wanted to avoid any possible ambiguity regarding the license. This will not cause a problem though, as I will show you exactly where and how to choose and download fonts for yourself. In addition to the graphics, sound, and fonts that we've come to expect, this game has two new asset types. They are level design files and GLSL shader programs. Let's find out about each of them. Levels are all created in a text file. By using the numbers 0 through 3, we can build level designs to challenge players. All the level designs are in the Levels folder in the same directory as the other assets. In addition to these level design assets, we have a special type of graphical asset called shaders. Shaders are programs written in GLSL, Graphics Library Shading Language. Don't worry about having to learn another language, as we don't need to get too in-depth to take advantage of shaders. Shaders are special, as they are entire programs separate from our C++ code, which are executed by the GPU each and every frame. In fact, some of these shader programs are run every frame for every pixel. Let's see how we're going to use the assets. The graphical assets make up the parts of the scene of our game. Take a look at the graphical assets, and it should be clear where in our game they will be used. If the tiles on the tiles_sheet graphic look a little different, this is because they are partly transparent and the background showing through changes them a little. If the background graphic looks totally different to the actual background in the game, that is because the shader programs we will write will manipulate each and every pixel, each and every frame, to create a kind of molten effect. Now for the sound assets. These are all .wave format. These are files that contain the sound effects we will play at certain events throughout the game. First, fall and fire.wave, a sound that will be played when the player's head goes into the fire and the player has no chance of escape. Fall and water.wave. Water has the same end effect as fire, death. This sound effect notifies the player they need to start from the beginning of the level. Fire1.wave. This sound effect is recorded in mono. It will be played at different volumes based on the player's distance from fire tiles and from different speakers based on whether the player is to the left or the right of the fire tile. Clearly, we will need to learn a few more tricks to implement this functionality. Jump.wave. A pleasing, slightly predictable whooping sound for when the player jumps. ReachGoal.wave. A pleasing victory sound for when the player or players gets both characters, Thomas and Bob, to the goal tile. Now that we've decided which assets we'll use, it is time to add them to the project. In case you're using different assets, simply replace the appropriate sound or graphic file with your chosen file using exactly the same file name. First, we have to browse to the visual directory. My project directory is highlighted here. This is the TWL subfolder. Create 5 new folders within this folder and name them as Fonts, Graphics, Levels, Shaders, and Sound. Now, from the download bundle, copy the entire contents of Section 1 into the TWL Graphics folder. I've copied and pasted them here. Similarly, copy the entire contents of Sound folder from the download bundle into the TWL Sound folder. You can see I've pasted the entire content of Sound folder here. Now for the fonts, visit dafont.com in your web browser, and then download the Roboto Light font. You'll get this roboto.zip file. Extract the contents of the zipped download. This is the folder created after extraction. In this folder, select the roboto-light.ttf file. Copy this to our Fonts folder. We are done with Fonts, Graphics, and Sound. Now we're left with Levels and Shaders. From the download bundle, copy the entire contents of Section 1, Levels, into our Levels folder. Similarly for Shaders, from the download bundle, copy the entire contents of Section 1, Shaders, into our Shaders folder. Now that we have a new project along with all the assets we will need for the entire project, we can talk about how we will structure the game engine code. In this video, we've looked at the Thomas Was Late game, creating the project, and from template, and the project assets. Cool! Next, we'll see structuring the Thomas Was Late code. Hi! Welcome to Structuring the Thomas Was Late code. In the previous video, we looked at Thomas Was Late game. In this video, we're going to improve the manageability of the code in this project with the help of Engine class. One of the problems that has been quite pronounced in both projects so far is how long and unwieldy the code gets. OOP allows us to break our projects up into logical and manageable chunks called classes. We will make a big improvement to the manageability of the code in this project with the introduction of an Engine class. Among other functions, the Engine class will have 3 private functions. They are Input, Update, and Draw. This should sound very familiar. Each of these functions will hold a chunk of the code that was previously all in the main function. Each of these functions will be in a code file of its own. input.cpp, update.cpp, and draw.cpp respectively. There will also be one public function in the engine class, which can be called with an instance of engine. This function is run and will be responsible for calling input, update, and draw once for each frame of the game. Furthermore, because we have abstracted the major parts of the game engine to the engine class, we can also move many of the variables from main and make them members of engine. All we need to do to get our game engine fired up is create an instance of engine and call its run function. Here's a sneak preview of the super simple main function. Don't add this code just yet. To make our code even more manageable and readable, we will also abstract responsibility for big tasks, such as loading a level and collision detection to separate functions in separate code files. These two functions are load level and detect collisions. We will also code other functions to handle some of the new features of the Thomas Was Late project. We will cover them in detail as and when they occur. To further take advantage of OOP, we will delegate responsibility for particular areas of the game entirely to new classes. You probably remember that the sound and HUD code was quite lengthy in previous projects. We will build a sound manager and HUD class to handle these aspects in a cleaner manner. Exactly how they work will be explored in depth when we implement them. The game levels themselves are much more in-depth than previous games, so we'll also code a level manager class. As you would expect, the playable characters will be made with classes as well. For this project, however, we will learn some more C++ and implement a playable character class with all the common functionality of Thomas and Bob, and then Thomas and Bob classes, which will inherit this common functionality as well as implement their own unique functions and abilities. This, perhaps unsurprisingly, is called inheritance. I will go into more detail about inheritance in the next section. We will also implement a number of other classes to perform specific responsibilities. For example, we'll make some neat explosions using particle systems. You might also be able to guess that to do this, we will code a particle class and a particle system class. All of these classes will have instances that are members of the engine class. Doing things this way will make all the features of the game accessible from the game engine, but encapsulate the details into appropriate classes. The last thing to mention before we move on to see the actual code that will make the engine class is that we will reuse without any changes whatsoever the texture holder class, which we discussed and coded for the Zombie Arena game. Cool! In this video, we learned structuring the Thomas Was Late code. Next up, we'll see building the game engine. Hi! This video is about building the game engine. In the last video, we learned structuring the Thomas Was Late code. In this video, we're going to take a look at reusing the texture holder class codingengine.h and codingengine.cpp. As suggested in the previous discussion, we will code a class called engine that will control and bind together the different parts of the Thomas Was Late game. The first thing we will do is make the texture holder class from the previous project available in this one. The texture holder class that we discussed and coded for the Zombie Arena game will also be useful in this project. While it is possible to add the files textureholder.h and textureholder.cpp directly from the previous project without recoding them or recreating the files, I don't want to make the assumption that you haven't jumped straight to this project. I'll guide you through few steps along with the complete code listing to create the texture holder class. To create the texture holder class from scratch, right-click Header Files in the Solution Explorer and select Add New Item. In the Add New Item window, click headerfile.h and then in the name field type texture holder. So the name is textureholder.h. Finally, click the Add button. Now, add this code to textureholder.h. Notice that we have an include directive for map from the STL. Then, we declare a map that holds string and SFML texture key value pairs. This map is called m_textures. Now, this line of code is quite interesting. Here, we are declaring a static pointer to an object of type texture holder called m_s_instance. This means that the texture holder class has an object that is the same type as itself. Not only that, but because it is static, it can be used through the class itself without an instance of the class. When we code the related .cpp file, we will see how we use this. Now, in the public part of the class, we have the prototype for the constructor function, textureHolder. The constructor takes no arguments and, as usual, has no return type. This is the same as the default constructor. We're going to override the default constructor with a definition that makes our singleton work how we want it to. We have another function called getTexture. Let's look at the signature again and analyze exactly what is happening. First, notice that the function returns a reference to a texture. This means that getTexture will return a reference, which is efficient because it avoids making a copy of what could be a fairly large graphic. Also, notice the function is declared as static. This means the function can be used without an instance of the class. The function takes a string as a constant reference as a parameter. The effect of this is twofold. Firstly, the operation is efficient, and secondly, because the reference is constant, it can't be changed. Now, let's create textureHolder.cpp file. Right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File.cpp, and then in the name field, type textureHolder. Lastly, click the Add button. Add this highlighted code to the file. See, this is the whole code. In the code, first we initialize our pointer to type textureHolder to null PTR. This is a constructor function. Inside the constructor function, this line of code ensures that m_s_instance equals null PTR. If it doesn't, the game will exit execution. Then m_s_instance equals to this assigns the pointer to this instance. Now, consider where this code is taking place. The code is in constructor. The constructor is the way we create instance of an object from classes. So, effectively, we now have pointer to a textureHolder that points the one and only instance of itself. In this line of code, we get a reference to m_textures. Then, we attempt to get an iterator to key-value pair using the passed in file name. If we find a matching key, we return the texture using this line of code. Otherwise, first we create a new key-value pair using the file name, and then we add texture to map, and at last we return it to the calling code with the help of return texture. textureHolder class introduced lots of new concepts: singleton, static functions, constant references, auto keyword, and syntax. We can now get on with our new engine class. As usual, we will start with the header file, which holds the function declarations and member variables. Note that we will revisit this file throughout the project to add more functions and member variables. For now, we will just add the code that is necessary at this stage. Right-click Header Files in the Solution Explorer and select Add New Item. In the Add New Item window, click Header File.h, and then in the name field, type Engine. Then click the Add button. Add this highlighted code to the file. This code consists of various member variables as well as the function declarations. Take note of the function and variable names, as well as whether they are private or public. Let's go through all of the private variables and functions. textureHolder.th, the one and only instance of the textureHolder class. Tile size, a useful constant to remind us that each tile in the sprite sheet is 50 pixels wide and 50 pixels high. Verts in quad, a useful constant to make our manipulation of a vertex array less error-prone. There are, in fact, 4 vertices in a quad. Now we can't forget it. Gravity, an instant int value representing the number of pixels by which the game characters will be pushed downward each second. This is quite a fun value to play with once the game is done. We initialize it to 300, as this works well for our initial level designs. m_window, the usual render window object like we've had in all of our projects. Look at these SFML view objects: m_main view, m_left view, m_right view, m_bg main view, m_bg left view, m_bg right view, and m_HUD view. The first 3 view objects, that is m_main view, is for the full screen view. M_left view is for left split screen, and M_right view right split screen views of the game. Now, these three SFML view objects will draw the background behind. The last view object, M_HUD view, will be drawn on top of the appropriate combination of the other 6 views to display the score, the remaining time, and any messages to the players. Having 7 different view objects might imply complexity, but when you see how we deal with them as the section progresses, you will see they are quite straightforward. We will have the whole split screen, full screen conundrum sorted out by the end of this section. Sprite M_background sprite and texture M_background texture. This combination of SFML sprite and texture will be for showing and holding the background graphic from the graphics assets folder. M_playing. This boolean will keep the game engine informed about whether the level has started yet by pressing the Enter key. The player does not have the option to pause the game once they've started it. Now we have set M_playing to false. M_character1. When the screen is full screen, should it center on Thomas, M_character1 equal to true, or Bob, M_character1 equal to false? Initially, it is initialized to true, to center on Thomas. M_split screen. Is the game currently being played in split screen mode or not? We will use this variable to decide how exactly to use all the view objects we declared a few steps ago. M_time remaining variable. This float variable holds how much time is remaining to get to the goal of the current level. We have set it to 10 for the purposes of testing until we actually get to set a specific time for each level. M_game time total variable. This variable is an SFML time object. It keeps track of how long the game has been played for. M_new level required boolean variable. This variable keeps a check on whether the player has just completed or failed a level. We can then use it to trigger the loading of the next level or the restarting of the current level. We have set it to true. The input function. This function will handle all of the player's input, which in this game is entirely from the keyboard. At first glance, it would appear that it handles all the keyboard input directly. In this game, however, we will be handling keyboard input that directly affects Thomas or Bob within the Thomas and Bob classes directly. We will call the input function, and this function will directly handle keyboard inputs such as quitting, switching to split screen, and any other keyboard input. The update function. This function will do all the work that we previously did in the update section of the main function. We will also call some other functions from the update function in order to keep the code organized. If you look back at the code, you will see that it receives a float parameter, which will hold the fraction of a second that has passed since the previous time. This, of course, is just what we need to update all our game objects. The draw function. This function will hold all the code that used to go in the drawing section of the main function in previous projects. We will, however, have some drawing code that is not kept in this function when we look at other ways to draw with SFML. Let's run through all public constructor functions. The engine constructor function. As we've come to expect, this function will be called when we first declare an instance of engine. It will do all the setup and initialization of the class. We will see exactly what when we code the engine.cpp file. The run function. This is the only public function that we need to call. It will trigger the execution of input, update, and draw, which will do all the work. Next, we'll see the definition of all these functions and some of the variables in action. Let's get started by coding engine and run it in engine.cpp. Right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File.cpp, and then in the Name field, type Engine. Finally, click the Add button. In this file, add this entire code. We will add constructor engine and public run function. All other functions will go in their own .cpp file with a name that makes it clear which function goes where. This will not be a problem for compiling as long as we add appropriate include directive #include engine.h at the top of all files that contain function definition from engine class. We are now ready to code the .cpp file for the engine class. The code for this function will be in the engine.cpp file we just created. Here, we are adding necessary include directives. Much of the code we have seen before. For example, there are the usual lines of code to get the screen resolution as well as to create a render window. At the end of this code, we use the now familiar code to load a texture and assign it to a sprite. In this case, first we are loading the background.png texture and assigning it to m_background sprite. In this code in between, the four calls to the setViewPort function that need some explanation. The setViewPort function assigns a portion of the screen to an SFML view object. It doesn't work using pixel coordinates, however. It works using a ratio where 1 is the entire screen, width or height. The first two values in each call to setViewPort are the starting position, horizontally then vertically, and the last two are the ending position. Notice that the m_left view and m_bg left view are placed in exactly the same place, starting at virtually the far left, 0.001 of the screen, and ending 2/1000ths from the center, 0.498. The m_right view and m_bg right view are also in exactly the same position, starting just left of the previous two view objects, 0.5, and extending to almost the far right-hand side, 0.998 of the screen. Furthermore, all the views leave a tiny sliver of a gap at the top and bottom of the screen. When we draw these view objects on the screen on top of a white background, it will have the effect of splitting the screen with a thin white line between the two sides of the screen, as well as a thin white border around the edges. I've tried to represent this effect in this diagram. The best way to understand it is to finish this section, run the code, and see it in action. Let's take a look at coding the run function definition. Add this highlighted code in engine.cpp just after the constructor code. The run function is the center of our engine. It initiates all the other parts. First, we declare a clock object. Next, we have the familiar while window is open loop, which creates the game loop. Inside this while loop, we restart clock and save the time that the previous loop took in DT. Then, we keep track of the total time elapsed in m_GameTimeTotal. Here, declare and initialize a float to represent the fraction of a second that elapsed during the previous frame. Next, we call input function. Then, we call update passing in the elapsed time, dt, as seconds. And at last, we call draw function. All of this should look very familiar. What is new is that it is wrapped in the run function. Now, let's move on to coding the input function definition. Right-click Source Files in the Solution Explorer and select Add. In that, click on New Item. Now we have to select c++file.cpp and then in the name field type Input. So the name is now input.cpp. Finally, click the Add button. We're now ready to code the input function. Now we have to add this highlighted code. The code for this function will go in its own file. This is the entire highlighted code that we have to add in the input.cpp file. In this highlighted code, first we will use #include engine.h and prefix the function signature with engine to make sure the compiler is aware of our intentions. As usual, when the escape key is pressed, it closes the window and the game will quit. That is, whenever we press escape key, the game will be closed. When Enter key is pressed, it sets m_playing to true, and eventually this will have the effect of starting the level. The cube key press alternates the value of m_character1 between true and false. This key only has an effect in full screen mode. It will switch between Thomas and Bob being the center of the main view. When E key is pressed, it switches m_split screen between true and false. This will have the effect of switching between full screen and split screen views. The majority of this keyboard functionality will be fully working by the end of the section. We're getting close to being able to run our game engine. Next, let's code the update function. As usual, right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click c++file.cpp, and then in the name field, type Update. Lastly, click the Add button. We're now ready to write some code for the update function. Now, add this highlighted code. The code for update function goes in update.cpp. Just as we did earlier, we will use #include engine.h and prefix the function signature with engine to make sure the compiler is aware of our intentions. Notice that the update function receives the time the previous frame took as a parameter. This, of course, will be essential for the update function to fulfill its role. Then it checks the if condition m is playing. If yes, then it subtracts the time the previous frame took from m_time remaining. It checks whether time has run out, and if it has, it sets m_new level required to true. All this code is wrapped in an if statement that only executes when m_playing is true. The reason for this is because, as with the previous projects, we don't want time advancing and objects updating when the game is not started. We will build on this code as the project continues. Lastly, let's code the draw function definition right-click source files in the Solution Explorer and select Add New Item. Then select C++file.cpp and then in the name field type draw. Now the name is draw.cpp. Then click the Add button. We are now ready to add some code to the draw function. Now we'll add this code to the file to implement the draw function. The code for draw function will go in its own file. You can see we will use #include engine.h here also, and prefix the function signature with engine. In this highlighted line of code, we clear the screen. In this project, we clear the screen with white. What is new is the way the different drawing options are separated by a condition, which checks whether the screen is currently split or full. If the screen is not split, we draw the background sprite in the background view, that is m_bg main view, and then switch to the main full screen view, m_main view. Note that at the moment, we don't actually do any drawing in m_main view. On the other hand, if the screen is split, the code in the else block is executed, and we draw m_bg left view with the background sprite on the left of the screen, followed by switching to m_left view. Then, still in the else block, we draw m_bg right view with the background sprite on the right of the screen, followed by switching to m_right view. Outside the if-else structure, we run to m_HUD view. At this stage, we're not actually drawing anything in m_HUD view. At last, we call the display function to show everything we have just drawn. As with the other two input update of the three most significant functions, we will be back here at the draw function often. We will add new elements of our game that need to be drawn. You'll notice that each time we do, we will add code into each of the main, left, and right sections. Let's quickly recap the engine class and then we can fire it up. What we have achieved is the abstraction of all the code that used to be in the main function into the input, update, and draw functions. The continuous looping of these functions, as well as the timing, is handled by the run function. As you can see here, input.cpp, update.cpp, and draw.cpp tabs open in Visual Studio. I've organized them in order. We will revisit each of these functions throughout the course of the project to add more code. Now that we have the basic structure and functionality of the engine class, we can create an instance of it in the main function and see it in action. In this video, we've looked at building the game engine. Great! In the next video, we'll learn coding the main function. Hi! This is the last video of this section, coding the main function. In the previous video, we looked at building the game engine. In this video, we will code the main function to see the background of the game. Let's start with renaming the hello sfml.cpp file as main.cpp. First, right-click on the hello sfml file in the Solution Explorer and select Rename, and change the name to main.cpp. This will be the file that contains our main function and the code that instantiates the engine class. Add this highlighted code to main.cpp. First, we add an include directive for the engine class. Then, inside the main function, declare an instance of engine. Then call its run function. Everything will be handled by the engine class until the player quits and the execution returns to main and the return 0 statement. That was easy. Now we can run the game by clicking on Local Windows Debugger button and see the empty background, either full screen or split screen, which will eventually contain all the action. Here's the game so far in full screen mode, showing just the background. Now tap the E key, and you'll be able to see the screen neatly partitioned into two halves, ready for split-screen co-op gameplay. Take a look at the neatly partitioned two halves. Awesome! Cool! That marks the end of this section. In this section, we started off with an introduction to the final project, Thomas Was Late. We then moved on to structuring the Thomas Was Late code. In the later videos, we learned building the game engine and coding the main function. That's amazing! In the next section, we'll be learning about advanced OOP, inheritance and polymorphism. Hi, this is Section 2, Advanced OOP, Inheritance and Polymorphism. We'll begin this section by learning inheritance and polymorphism. Then, we'll take a look at abstract classes and building the playable character class. Lastly, we'll explore building the Thomas and Bob classes and updating the game engine to use Thomas and Bob. Now, let's get started with the first video of this section that deals with inheritance. In this video, we're going to take a look at: we have seen how we can use other people's hard work by instantiating creating objects from the classes of the SFML library. But what if there's a class that has loads of useful functionality in it, but is not quite what we want? In this situation, we can inherit from the other class. Just like it sounds, inheritance means we can harness all the features and benefits of other people's classes, including the encapsulation, while further refining or extending the code specifically to our situation. With all this in mind, let's take a look at an example class and see how we can extend it, just to see the syntax and as a first step. First, we define a class to inherit from. This is no different from how we created any of our other classes. Take a look at this hypothetical soldier class declaration. In this code, first we define a soldier class. It has 4 private variables: m_health, m_armor, m_range, and m_shot power. It has 4 public functions: set health, set armor, set range, and set shot power. We don't need to see the definition of the functions. They will simply initialize the appropriate variable that their name makes obvious. We can also imagine that a fully implemented soldier class would be much more in-depth than this. It would probably have functions such as shoot, go prone, and others. If we implemented a soldier class in an SFML project, it would likely have a sprite object, as well as an update and a get position function. Now, the simple scenario presented here is suitable for learning about inheritance. Look at this code, especially the highlighted part. By adding the public soldier code to the sniper class declaration, sniper inherits from soldier. But what does this mean exactly? Sniper is a soldier. It has all the variables and functions of soldier. Inheritance is more than this, however. Notice that in this code, we declare a sniper constructor. This constructor is unique to sniper. We have not only inherited from soldier, we have extended soldier. All the functionality, definitions of the soldier class, are handled by the soldier class, but the definition of the sniper constructor must be handled by the sniper class. This is what the hypothetical sniper constructor definition might look like. We could go ahead and write a bunch of other classes that are an extension of the soldier class, perhaps commando and infantryman. Each would have the exact same variables and functions, but each would also have a unique constructor that initializes those variables appropriate to the type of soldier. Commando might have a very high m_health and m_shot power, but really puny m_range. Infantryman might be in between commando and sniper, with mediocre values for each variable. The terminology we might like to learn here is that the class that is extended from superclass is the subclass. We can also say parent and child class. Let's now take a look at protected variables. There is an access specifier for class variables and functions called protected. You can think of protected variables as being somewhere between public and private. Here is a quick summary of access specifiers, along with more details about the protected specifier. Public variables and functions can be accessed and used by anyone. Private variables and functions can only be accessed, used by the internal code of the class. This is good for encapsulation, and when we need to access, change private variables, we can provide public getter and setter functions, such as getSprite and so on. If we extend a class that has private variables and functions, that child class cannot directly access the private data of its parent. Protected variables and functions are almost the same as private. They cannot be accessed, used directly by an instance of the class. However, they can be used directly by any class that extends the class they are declared in. So it is like they're private except to child classes. To fully understand what protected variables and functions are and how they can be useful, we'll look at another topic first before we can see them in action. In this video, we've learned about inheritance. Cool! In the next video, we'll take a look at polymorphism. Hi, welcome to the second video of this section, polymorphism. In the previous video, we learned about inheritance. In this video, we'll go through the concept of polymorphism and take a look at an example. Polymorphism allows us to write code that is less dependent on the types we are trying to manipulate. This can make our code clearer and more efficient. It means different forms. If the objects that we code can be more than one type of thing, then we can take advantage of this. Boiled down to its simplest definition, polymorphism is this. Any subclass can be used as a part of the code that uses the superclass. This means we can write code that is simpler and easier to understand, and also easier to modify or change. Also, we can write code for the superclass and rely on the fact that no matter how many times it is subclassed within certain parameters, the code will still work. Let's discuss an example. Suppose we want to use polymorphism to help write a zoo management game where we have to feed and tend to the needs of animals. We will probably want to have a function such as feed. We will also probably want to pass an instance of the animal to be fed into the feed function. A zoo, of course, has many types of animals: lion, elephant, and three-toed sloth. With our new knowledge of C++ inheritance, it will make sense to code an animal class and have all the different types of animal inherit from it. If we want to write a function, feed, that we can pass lion, elephant, and three-toed sloth into as a parameter, it might seem like we need to write a feed function for each and every type of animal. However, we can write polymorphic functions with polymorphic return types and arguments. Take a look at this definition of the hypothetical feed function. This function has the animal reference as a parameter, meaning that any object that is built from a class that extends animal can be passed into it. So you can even write code today and make another subclass in a week, month, or year, and the very same functions and data structures will still work. Also, we can enforce upon our subclasses a set of rules for what they can and cannot do, as well as how they do it. So good design in one stage can influence it at other stages. But will we really ever want to instantiate an actual animal? We'll find out. In this video, we've looked at polymorphism. Great! Next, as I just said, we'll see abstract classes, virtual and pure virtual functions. Hi, this is Abstract Classes, Virtual and Pure Virtual Functions. In the previous video, we got to know about polymorphism. In this video, we'll make a class abstract and try and understand abstract classes with an example. An abstract class is a class that cannot be instantiated and therefore cannot be made into an object. So it's code that will never be used then. No, that's like paying an architect to design your home and then never building it. If we, or the designer of a class, want to force its users to inherit it before using their class, they can make a class abstract. Then we cannot make an object from it. Therefore, we must extend it first and make an object from the subclass. To do so, we can make a function pure virtual and not provide any definition. Then, that function must be overridden, rewritten in any class that extends it. Let's take a look at an example. It will help. We make a class abstract by adding a pure virtual function, such as this abstract animal class that can only perform the generic action of make noise. As you can see, we add the C++ keyword, virtual before, and equal to 0 after the function declaration. Now, any class that extends inherits from animal must override the make noise function. This might make sense, since different types of animal make very different types of noise. We could perhaps have assumed that anybody who extends the animal class is smart enough to notice that the animal class cannot make a noise and that they will need to handle it. But what if they don't notice? The point is that by making a pure virtual function, we guarantee that they will, because they have to. Abstract classes are also useful because sometimes we want a class that can be used as a polymorphic type, but we need to guarantee it can never be used as an object. For example, animal doesn't really make sense on its own. We don't talk about animals, we talk about types of animal. We don't say, oh, look at that lovely fluffy white animal, or yesterday we went to the pet shop and got an animal and an animal bed. It's just too, well, abstract. So, an abstract class is kind of like a template to be used by any class that extends it, inherits from it. If we were building an industrial empire-type game where the player manages businesses and their employees, we might want a worker class, for example, and extend it to make miner, steelworker, office worker, and of course, programmer. But what exactly does a plain worker do? Why would we ever want to instantiate one? The answer is, we wouldn't want to instantiate one, but we might want to use it as a polymorphic type so we can pass multiple worker subclasses between functions and have data structures that can hold all types of workers. All pure virtual functions must be overridden by any class that extends the parent class that contains the pure virtual function. This means that the abstract class can provide some of the common functionality that would be available in all its subclasses. For example, the worker class might have the M_annual salary, M_productivity, and M_age member variables. It might also have the getPayCheck function, which is not pure virtual and is the same in all the subclasses. But it might have a doWork function, which is pure virtual and must be overridden because all the different types of worker will do work very differently. By the way, virtual, as opposed to pure virtual, is a function that can be optionally overridden. You declare a virtual function the same way as a pure virtual function, but leave the equal to 0 off the end. In the current game project, we will use a pure virtual function. If any of this virtual, pure virtual, or abstract stuff is unclear, using it is probably the best way to understand it. In this video, we have learned about abstract classes, virtual and pure virtual functions. Awesome! Next up, we'll see the building the playable character class. Hi! Welcome to Building the Playable Character class. Previously, we looked at abstract classes, virtual and pure virtual functions. In this video, we're going to take a look at coding playablecharacter.h and playablecharacter.cpp. Now that we know the basics about inheritance, polymorphism, and pure virtual functions, let's put them to use. We will build a playable character class that has the vast majority of the functionality that any character from our game is going to need. It will have one pure virtual function, handle input. The handle input function will need to be quite different in the subclasses, so this makes sense. As playable character will have a pure virtual function. It will be an abstract class and no objects of it will be possible. We will then build both Thomas and Bob classes, which will inherit from playable character, implement the definition of the pure virtual function, and allow us to instantiate Bob and Thomas objects in our game. Let's start with coding playablecharacter.h. Right-click Header Files in the Solution Explorer and select Add New Item. In the Add New Item window, click headerfile.h and then in the name field type playable character. So, now the name is playablecharacter.h. Lastly, click the Add button. We are now ready to code the header file for the playable character class. Add this highlighted code in the file. As usual, when creating a class, we will start off with the header file that will contain the member variables and function declarations. What is new is that in this class, we will declare some protected member variables. Remember that protected variables can be used as if they are public by classes, which inherit from the class with the protected variables. We will add and discuss the contents of the playablecharacter.h file in 3 sections. First, the protected section, followed by private, then public. The first thing to notice in the code we just wrote is that all the variables are protected. This means that when we extend the class, all the variables we just wrote will be accessible to those classes that extend it. We will extend this class with Thomas and Bob classes. Apart from the protected access specification, there's nothing new or complicated about this code. It is worth paying attention to some of the details, however. Then, it will be easy to understand how the class works as we progress. So let's run through those protected variables one at a time. First of all, we have our somewhat predictable sprite, m_sprite. That is, we are declaring an object of sprite called m_sprite. We have a float called m_jump duration, which will hold a value representing the time that the character is able to jump for. The greater the value, the higher the character will be able to jump. Next, we have a boolean, m_is_jumping, which is true when the character is jumping and false otherwise. This will be useful for making sure that the character can't jump while in midair. The m_is_falling variable has a similar use to m_is_jumping. It will be useful to know when a character is falling. It's also a boolean variable. Next, we have two booleans that will be true if the character's left or right keyboard buttons are currently being pressed. These are relative depending upon the character, keys A and D for Thomas, left and right arrow keys for Bob. How we respond to these booleans will be seen in the Thomas and Bob classes. The m_timeThisJump float variable is updated each and every frame that m_ is jumping is true. We can then know when m_jump duration has been reached. The final protected variable is the boolean m_justJumped. This will be true if a jump was initiated in the current frame. It will be useful for knowing when to play a jump sound effect. As of now, we have set m_justJumped to false. Next, add this highlighted code where we are adding private variables to the playable character.h file. We have some interesting private variables here. Remember that these variables will only be directly accessible to the code in the playable character class. The Thomas and Bob classes will not be able to access them directly. The m_gravity variable will hold the number of pixels per second that the character will fall. The m_speed variable will hold the number of pixels per second that the character can move left or right. The vector2f m_position variable is the position in the world, not the screen, where the center of the character is. The next four float rect objects are important to discuss. When we did collision detection in the Zombie Arena game, we simply checked to see if two float rect objects intersected. Each float rect object represented an entire character, a pickup, or a bullet. For the non-rectangular shaped objects, zombies and the player, this was a little bit inaccurate. In this game, we will need to be more precise. The m_feet, m_head, m_right, and m_left float rect objects will hold the coordinates of the different parts of a character's body. These coordinates will be updated in each and every frame. Through these coordinates, we'll be able to tell exactly when a character lands on a platform, bumps his head during a jump, or rubs shoulders with a tile to his side. Lastly, we have texture. That is, we declare an object of type texture called m_texture. Texture is private, as it is not used directly by the Thomas or Bob classes, but as we saw, sprite is protected because it is used directly. Now, add all the public functions to the playable character.h file. This is the entire highlighted code to be added. Let's talk about each of the function declarations that we just added. This will make coding their definitions easier to follow. First, the spawn function receives a vector2f called startPosition and a float called gravity. As the name suggests, start position will be the coordinates in the level at which the character will start, and gravity will be the number of pixels per second at which the character will fall. The bool virtual handle input equals to 0 is, of course, our pure virtual function. As playable character has this function, any class that extends it, if we want to instantiate it, must provide a definition for this function. Therefore, when we write all the function definitions for playable character in a minute, we will not provide a definition for handle input. There will, of course, need to be definitions in both the Thomas and Bob classes. The getPosition function returns a float rect that represents the position of the whole character. The getFeet function, as well as getHead, getRight, and getLeft, each return a float rect that represents the location of a specific part of the character's body. This is just what we need for detailed collision detection. The getSprite function, as usual, returns a copy of m_sprite to the calling code. The stopFalling, stopRight, and stopLeft receive a single float value, which the function will use to reposition the character and stop it walking or jumping through a solid tile. The stop-jump function will stop the character from jumping through a solid tile. The getCenter function returns a vector 2f to the calling code to let it know exactly where the center of the character is. This value is, of course, held in m_position. We will see later that it is used by the engine class to center the appropriate view around the appropriate character. The update function we have seen many times before, and as usual, it takes float parameter, which is the fraction of a second that the current frame has taken. This update function will need to do more work than previous update functions from other projects. However, it will need to handle jumping as well as updating the float rect objects that represent the head, feet, left, and right. Now we can write the definitions for all the functions, except of course handle input. Now let's move on to coding playablecharacter.cpp. Just like we always do, right-click Source Files in the Solution Explorer and select Add New Item. Click C++file.cpp and then in the name field type Playable Character and click Add. We are now ready to code the .cpp file for the Playable Character class. We will break up the code and discussion into a number of chunks. First, add the include directives and the definition of the spawn function. The spawn function initializes m_position with the passed in position. That is, m_position x equals start position x and m_position y equals start position y. It also initializes m_gravity, and this final line of code moves m_sprite to its starting position. Next, add the definition for the update function. Add this entire highlighted code immediately after the preceding code. Here, first we check whether m_right pressed is true. If it is, m_position is changed using this formula, m_speed into elapsed time. Same is done for m_left pressed. In case it's true, it changes m_position using this formula. Then we see whether or not the character is currently executing a jump. If this if statement is true, the code first updates m_time this jump with elapsed time. Then it checks if m_time this jump is still less than m_jump duration. If it is, change the y-coordinate of m_position by twice gravity multiplied by the elapsed time. In the else clause, it executes when m_time this jump is not lower than m_jump duration. Then m_falling is set to true. Also, m_jumping is set to false. This prevents the code we have just been discussing from executing, as if m_is jumping is now false. Next, if m_is falling block moves m_position down each frame, it is moved using the current value of m_gravity and the elapsed time. That is, using the current value of m_gravity and the elapsed time. This code, which is almost all of the remaining code, updates the body parts of the character relative to the current position of the sprite as a whole. Take a look at this diagram to see how the code calculates the position of the virtual head, feet, left, and right sides of the character. This final line of code uses the setPosition function to move the sprite to its corrected location after all the possibilities of the update function. Now, add this code right after the previous one. Here, we are adding the definition for the getPosition, getCenter, getFeet, getHead, getLeft, getRight, and getSprite functions. The getPosition function returns a float rect that wraps the entire sprite, and getCenter returns a vector 2f, which contains the center of the sprite. Notice that we divide the height and width of the sprite by 2 in order to dynamically arrive at this result. This is because Thomas and Bob will be of different heights. The getFeet, getHead, getLeft, and getRight functions return the float rect objects that represent the body parts of the character that we update each frame in the update function. The getSprite function, as usual, returns a copy of m_sprite. Finally, for the playable character class, add the definitions for the stop falling, stop right, stop left, and stop jump functions. Note that to do so immediately after the previous code. Each of these functions receive a value as a parameter that is used to reposition either the top, bottom, left, or right of the sprite. Exactly what these values are and how they are obtained will be seen later. Each of the previous functions also repositions the sprite. The final function is the stop-jump function that will also be used in collision detection. It sets the necessary values for m underscore is jumping and m underscore is falling to end a jump. Here we have set m underscore is jumping to false and m underscore is jumping to true. In this video, we have learned building the playable character class. Cool! In the next video, we'll see building the Thomas and Bob classes. This is building the Thomas and Bob classes. In the last video, we looked at building the playable character class. In this video, we're going to take a look at coding Thomas.h, Thomas.cpp, Bob.h, and Bob.cpp. Now we get to use inheritance for real. We will build a class for Thomas and a class for Bob. They will both inherit from the playable character class we just coded. They will then have all the functionality of the playable character class, including direct access to its protected variables. We will also add the definition for the pure virtual function handle input. You will notice that the handle input functions for Thomas and Bob will be different. Let's start with coding Thomas.h. Right-click Header Files in the Solution Explorer and select Add New Item. Then highlight by left-clicking headerfile.h and then in the name field type Thomas. Click Add button at the end. We're now ready to code the header file for the Thomas class. Now, add this code to the Thomas.h class. The code is very short and sweet. The Thomas class is inheriting from the playable character class we have just coded. It will have all of the functionality of the playable character class. Here, you can see that we have a constructor and notice that we have added the definition of the pure virtual handle input function. And now we're going to implement it. So, moving on to coding Thomas.cpp. Right-click Source Files in the Solution Explorer and select Add New Item. In this window, click C++ File and then in the name field type Thomas. So you have the file name Thomas.cpp. Click Add. We can now code the .cpp file for the Thomas class. Add the Thomas constructor to the file as I just did. Now, in this code, first we add the necessary include directives, and this is the constructor function, Thomas. Here we load the Thomas.png graphics and then set the duration of a jump, m_jump duration, to 0.45, nearly half a second. Now, add the definition of the handle input function. This highlighted code should look quite familiar. We are using the sfml is key pressed function to see whether any of the W, A, or D keys are pressed. Now, when W key is pressed, the player is attempting to jump. The code then uses the if not m underscore is jumping and not m underscore is falling condition, which checks that the character is not already jumping and that it is not falling either. When these tests are both true, m underscore is jumping is set to true. M underscore time this jump is set to 0, and M underscore just jumped is set to true. When the previous two tests don't evaluate to true, the else clause is executed, and M underscore jumping is set to false, and M underscore is falling is set to true. Now, the handling of the A and D keys being pressed is as simple as setting M underscore left pressed or M underscore right pressed to true or false. The update function will now be able to handle moving the character. The last line of code in the function returns the value of M underscore just jumped. This will let the calling code know if it needs to play a jumping sound effect. We will now code the Bob class, although this is nearly identical to the Thomas class, except it has different jumping abilities, a different texture, and uses different keys on the keyboard. For coding Bob.h, right-click Header Files in the Solution Explorer and click Add New Item. Then click headerfile.h and then in the name field type Bob. Lastly, click Add button. Now let's code the header file for the Bob class. Add this highlighted code to the file. First, we've added the necessary include directives. See that the Bob class is identical in structure to the Thomas class. It inherits from playable character, and it has a constructor, same as the class name Bob. The difference compared to Thomas is that we initialize some of Bob's member variables differently, and we handle input in the handle input function differently as well. Now, moving on to coding Bob.cpp. Just as we always do, right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File and then in the name field type Bob. Finally, click Add. So we are now ready to code the .cpp file for the Bob class. Nom. Add this code for the Bob constructor to the file. This is the Bob constructor. Notice that the texture is different, bob.png, and that m_jump duration is initialized to a significantly smaller value, that is 0.25. Bob is now his own unique self. Now, add the handle input code immediately after the Bob constructor. I've highlighted the whole code. Notice that the code is nearly identical to the code in the handle input function of the Thomas class. The only difference is that we respond to different keys, up arrow key for jump, the left arrow key, and the right arrow key. Now we have a playable character class that has been extended by Bob and Thomas. We can add a Bob and Thomas instance to the game. Cool! In this video, we have learned building the Thomas and Bob classes. Great! Next up, we'll update the game engine to use Thomas and Bob. Hi! This is the last video of this section, updating the game engine to use Thomas and Bob. In the previous video, we looked at building Thomas and Bob classes. In this video, we'll be updating engine.h, the input function, the update function, and also we'll draw Bob and Thomas. In order to be able to run the game and see our new characters, we have to declare instances of them, call their spawn functions, update them each frame, and draw them each frame. Let's start with declaring their instances now. So, open up the engine.h file and add the include directives first. #include thomas.h, #include bob.h. Now, inside private section after texture holder th, write a comment, Thomas and his friend Bob. Then, Thomas, m_Thomas, and Bob, m_Bob. So, we have an instance of both Thomas and Bob, which are derived from playable character. Now, we'll add the ability to control the two characters. The code we'll add will go in the input part. Of course, for this project, we have a dedicated input function. Open up input.cpp and add this highlighted code. Note that the code has all the functionality as contained with the Thomas and Bob classes. All the code has to do is add an include directive for each of the Thomas and Bob classes. Then, within the input function, the code just calls the pure virtual handle input functions on m_Thomas and m_Bob. The reason we wrap each of the calls in an if statement is because they return true or false based upon whether a new jump has just been successfully initiated. We will handle playing the jump sound effects in Section 4, Sound Spatialization and HUD. Let's move on to updating the update function to spawn and update the playable character instances. This is broken down into two parts. First, we need to spawn Bob and Thomas at the start of a new level, and second, we need to update by calling their update functions each frame. We need to call the spawn functions of our Thomas and Bob objects in a few different places as the project progresses. Most obviously, we need to spawn the two characters when a new level begins. In this section, as the number of tasks we need to perform at the beginning of a level increases, we will write a load level function. For now, let's just call spawn on m_Thomas and m_Bob in the update function, as seen in this highlighted code. Add the code, but keep in mind that this code will eventually be deleted and replaced. The entire code is wrapped in an if statement that checks whether a new level is required. Then, this code simply calls spawn and passes in a location in the game world along with the gravity. The actual spawning code will be moved to a dedicated load level function, but the if condition will be part of the finished project. Also, m_time remaining is set to an arbitrary 10 seconds. And here, we set m_new level required to false. Next, we update Thomas and Bob. So, inside the if loop for condition m_playing, add a comment. Update Thomas, then m_Thomas.updateDT as seconds. Similarly, update Bob, m_BobUpdate.dt as seconds. All we do here is call their update functions and pass in the time this frame has taken. Now that the characters can move, we need to update the appropriate view objects to center around the characters and make them the center of attention. Of course, until we have some objects in our game world, the sensation of actual movement will not be achieved. Add this highlighted code just after end if playing comment. The code handles the two possible situations. First, the if M split screen condition positions the left-hand view around M_Thomas, and here it positions the right-hand view around M_Bob. The else clause that executes when the game is in full screen mode tests to see if M_character1 is true. If it is, then the full screen view, M_main view, is centered around Thomas. Otherwise, in else condition, it is centered around Bob. You probably remember that the player can use the E key to toggle split screen mode and the Q key to toggle between Bob and Thomas in full screen mode. We coded this in the input function of the engine class back in the previous section, Abstraction and Code Management, making better use of OOP. Now let's draw Bob and Thomas. Make sure the draw.cpp file is open, and then, if not equal to M_split screen, after M_window set view, write a comment. Draw Thomas M_window.draw M_Thomas.getSprite. In the same way, draw Bob. M_window.draw M_Bob.getSprite. Notice that we drew both Thomas and Bob for the full screen. Now we'll draw them for left and right. After M_window set view, write comment draw Bob M_window.draw M_Bob.getSprite. Similarly, draw Thomas. M_window.draw M_Thomas.getSprite. Here we have drawn Thomas and Bob for left view. Now, note the very subtle difference in the way that we draw the characters in split screen mode. When drawing the left side of the screen, we switch the order the characters are drawn and draw Thomas after Bob, so Thomas will always be on top on the left and Bob on the right. This is because the player controlling Thomas is catered for on the left and Bob the right. You can run the game by clicking on Local Windows Debugger button. You can move Bob with the help of arrow keys. See, he moves towards left and right. If you press the Q key to switch focus from Bob to Thomas, you can move Thomas using keys A and D. I'm moving Thomas to the left using key A, and to the right using D key. If you move either of the characters left or right, you will see them move relative to each other. Now, try pressing the E key to toggle between full screen and split screen. This is the split screen. Then, try moving both characters again to see the effect. You can see that Thomas is always centered in the left-hand window, and Bob is always centered in the right-hand window. If you leave the game running long enough, the characters will respawn in their original positions every 10 seconds, as you can see here. This is the beginning of the functionality we will need for the finished game. This behavior is caused by M_time remaining going below 0 and then setting the M_new level required variable to true. Also note that we can't see the full effect of movement until we draw the details of the level. In fact, although it can't be seen, both characters are continuously falling at 300 pixels per second. As the camera is centering around them every frame and there are no other objects in the game world, we cannot see this downward movement. If you want to demonstrate this to yourself, in update.cpp, just change the call to m_bob.spawn. Change this 100 to 0 and gravity to 0. Now that Bob has no gravitational effect, he will move in upward direction. Thomas will visibly fall away from him. We will add some playable levels to interact with in the next section. In this video, we've updated the game engine to use Thomas and Bob. Amazing! In this section, we started off by learning inheritance and polymorphism, then looked at abstract classes and building the playable character class. Lastly, we explored building the Thomas and Bob classes and updating the game engine to use Thomas and Bob. Awesome! In the next section, we'll learn building playable levels and collision detection. Welcome to the third section of this course, Building Playable Levels and Collision Detection. We'll start this section by designing levels in a text file. We would then build a level manager class that will load levels from a text file, convert them into data our game can use, and keep track of the level details, such as spawn position, current level, and allowed time limit. Then, we'll update the game engine to use Level Manager, and lastly, we'll code a polymorphic function to handle the collision detection for both Bob and Thomas. Now, we start with the first video of this section, designing some levels. In this video, we're going to take a look at the code and images for level designs. Remember our sprite sheet that we introduced in Section 1, Abstraction and Code Management? Here it is again, annotated with numbers that represent each tile that we will build our levels from. I placed the screenshot on a gray background so you could see clearly the different details of the sprite sheet. The checkered background represents the level of transparency, so all of the tiles except for number 1 will reveal at least a little of the background behind them. Tile 0 is completely transparent and will be used to fill in the gaps where there aren't any other tiles. Tile 1 is for the platforms that Thomas and Bob will walk on. Tile 2 is for fire tiles, and Tile 3 is for water tiles. Tile 4 you might need to look quite closely to see. It has a white square outline. This is the goal of the level, where Thomas and Bob must get to together. Keep this image in mind as we discuss designing the levels. We will enter combinations of these tile numbers into text files to design the layouts. Here's an example that will help. This code translates to the level layout shown here. Note that to get the view shown, I had to zoom out the view. Also, the image is cropped. The actual start of the level would look like this. The first point of showing you these images is twofold. Firstly, you can see how you can quickly construct level designs using a simple and free text editor. Secondly, it demonstrates the gameplay aspects of the design. From left to right in the level, Thomas and Bob first need to jump a small hole or they'll fall to their deaths, respawn. Then they have a large expanse of fire to traverse. It is actually impossible for Bob to jump that many tiles. The players will need to work together for the solution. The only way that Bob will clear the fire tiles is by standing on Thomas's head and jumping from there, as you can see here. It is then quite simple to get to the goal and move on to the next level. I strongly encourage you to complete this section and then spend some time designing your own levels. I've included a few level designs to get you started. They are in the Levels folder that we added to the project back in Section 1, Abstraction and Code Management. You can see them here. Let's see some zoomed out views of the game along with the code of the level design. The code is probably more useful than reproducing the actual textual content. If you do want to see the code, just open up the files in the Levels folder. This is the Levels folder, and this is what the code looks like. See, this is level layout that the previous code will produce. Look at this image. This level is the Leap of Faith, level I, referred to in Section 1. I have highlighted the platforms as they are not very clear in the zoomed out image. The provided designs are simple. The game engine will be able to handle very large designs, however. You have the freedom to use your imagination and build some really big and hard to complete levels. Of course, these designs won't actually do anything until we learn how to load them and convert the text into a playable level. Additionally, it won't be possible to stand on any platforms until we have implemented the collision detection. So, we'll move to loading the level designs. In this video, we have designed levels. Great! In the next video, we'll take a look at building the Level Manager class. Hi! This video is building the Level Manager class. In the previous video, we learned about designing levels. In this video, we're going to code levelmanager.h and levelmanager.cpp. It will take several phases of coding to make our level designs work. The first thing we will do is code the Level Manager header file. This will allow us to look at and discuss the member variables and functions that will be in the Level Manager class. Next, we will code the levelmanager.cpp file, which will have all the function definitions in it. As this is a long file, we will break it up into several sections to code and discuss them. Once the Level Manager class is complete, we will add an instance of it to the game engine class. We will also add a new function to the engine class, load level, which we can call from the update function whenever a new level is required. The load level function will not only use the level manager instance to load the appropriate level, but it will also take care of aspects such as spawning the player characters and preparing the clock. As already mentioned, let's get an overview of Level Manager by coding the levelmanager.h file. Create a .h file as always. Right-click Header Files in the Solution Explorer and select Add New Item. Click Header File .h and then in the name field type Level Manager. Lastly, click Add. We are now ready to code the header file for the Level Manager class. Now add this highlighted code to the file. It consists of necessary include directives and private variables. Here, we're adding an include directive called sfmlgraphics.hpp. Then, we are using namespace sf and namespace std. In the Level Manager class, these are the various private variables. The code first declares vector 2i m_level size to hold two integer values that will hold the horizontal and vertical number of tiles that the current map contains. Vector 2f m_start position contains the coordinates in the world where Bob and Thomas should be spawned. Note that this is not a tile position relatable to m_level size units, but a horizontal and vertical pixel position in the level. The m_time modifier member variable is a float that will be used to multiply the time available in the current level. The reason we want to do this is so that by decreasing this value, we will shorten the time available each time the player attempts the same level. As an example, if the player gets 60 seconds for the first time they attempt level 1, then 60 multiplied by 1 is of course 60. When the player completes all the levels and comes back to level 1 for the second time, m_time modifier will have been reduced by 10%. Then, when the time available is multiplied by 0.9, the amount of time available to the player will be 54 seconds. This is 10% less than 60. The game will get steadily harder. The float variable m_base time limit holds the original unmodified time limit we have just been discussing. You can probably guess that m_current level will hold the current level number that is being played. The int num_levels constant will be used to flag when it is appropriate to go back to level 1 again and reduce the value of m_time modifier. Next, add this highlighted code, which consists public variables and function declarations. Let's go through it. Notice that there are two constant int members. Tile_size is a useful constant to remind us that each tile in the sprite sheet is 50 pixels wide and 50 pixels high. verts_in_quad is a useful constant to make our manipulation of a vertex array less error-prone. There are, in fact, 4 vertices in a quad. Now, we can't forget it. The getTimeLimit, getStartPosition, getLevelSize, and getCurrentLevel functions are simple getter functions that return the current value of the private member variables we declared in the previous block of code. A function that deserves a closer look is nextLevel. This function receives a vertex array reference, just like we used in the Zombie Arena game. The function can then work on the vertex array, and all the changes will be present in the vertex array from the calling code. The nextLevel function returns a pointer to a pointer, which means we can return an address that is the first segment of a two-dimensional array of int values. We will be building a two-dimensional array of int values that will represent the layout of each level. Of course, these int values will be read from the level design text files. Now, we'll code the levelmanager.cpp file. Right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, select C++ File and then rename the file to Level Manager. Lastly, click Add. We are now ready to code the .cpp file for the Level Manager class. As this is quite a long class, we'll break it up to discuss it in 6 chunks. The first 5 will cover the next level function and the 6th all the rest. Add this highlighted code. Here, we are adding shows include directives and the first of 5 part of the next level function. After the include directives, the code initializes m_levelSize.x and m_levelSize.y to 0. Next, m_current level is incremented. The if statement that follows checks whether m_current level is greater than num_levels. If it is, m_current level is set back to 0 and m_time modifier is reduced by 0.1f in order to shorten the time allowed for all levels. The code then switches based on the value held by m_current level. Each case statement initializes the name of the text file, which holds the level design, and the starting position for Thomas and Bob, as well as m_base time limit, which is the unmodified time limit for the level in question. Now, add the second part of the next level function. Add this highlighted code immediately after the previous code. We'll go through it in detail. First, we declare an if stream object called input_file, which opens a stream to the file name contained in level to load. The code loops through each line of the file using getLine, but doesn't record any of its content. All it does is count the number of lines by incrementing m_levelSize.y. After the while loop, the width of the level is saved in m_levelSize.x using s.length. This implies that the length of all the lines must be the same, or we would run into trouble. At this point, we know and have saved the length and width of the current level in m_levelSize. Now, add the third part of the next level function. Add this code immediately after the previous code. Here, we clear input_file using its clear function. The seek_g function called with the 0 iOS_beg parameters resets the stream back to before the first character. Next, we declare a pointer to a pointer called array_level. Note that this is done on the free store or heap using the new keyword. Once we have initialized this two-dimensional array, we will be able to return its address to the calling code, and it will persist until we either delete it or the game is closed. This is for loop loops from 0 to m_levelSize.y-1. In each pass, it adds a new array of int values to the heap to match the value of m_levelSize.x. We now have a perfectly configured, for the current level, two-dimensional array. The only problem is that there's nothing in it. Next, we add the fourth part of the next level function. Add this code immediately after the previous code. First, the code initializes a string called row, which will hold one row of the level design at a time. We also declare and initialize an int called y that will help us count the rows. The while loop executes repeatedly until input_file gets past the last row. Inside the while loop, there is a for loop, which goes through each character of the current row and stores it in the two-dimensional array_level. Notice that we access exactly the right element of the two-dimensional array with array_level, array of y and x. The a to I function converts char val to int. This is what is required because we have a two-dimensional array for int, not char. Over here, we increment y, and lastly, close the file. Now, add the fifth part of the next level function. Add the code right after the previous one. This is entire highlighted code. Just after, close the file. Although this is the longest section of code from the 5 sections we divided next level into, it is also the most straightforward. What happens is that the nested for loop loops from 0 through to the width and height of the level. For each position in the array, 4 vertices are put into vertex array, and 4 texture coordinates are assigned from the sprite sheet. The positions of the vertices and texture coordinates are calculated using the current vertex available, the tile size, and verts_in_quad constants. At the end of each loop of the inner for loop, current vertex is increased by verts_in_quad, moving nicely on to the next tile. The important thing to remember about this vertex array is that it was passed into next level by reference. Therefore, the vertex array will be available in the calling code. We will call next level from the code in the engine class. Once this function has been called, the engine class will have a vertex array to represent the level graphically, a two-dimensional array of int values as a numerical representation of all the platforms and obstacles in the level. The last part is remaining now. You have to add this highlighted code after the end of next level function. Here, we are adding rest of the functions from Level Manager class. These Level Manager functions are all simple getter functions, but do take the time to familiarize yourself with what private value is returned by which function. Now that the Level Manager class is complete, we can move on to using it. We will code another function in the engine class to do so. Cool! In this video, we have learned building the Level Manager class. Next up, we'll code the load level function. Coding the load level function. In the previous video, we learned building the Level Manager class. In this video, we'll add the declaration and the code for the load level function. To be clear, this function is part of the engine class, although it will delegate much of its work to other functions, including those of the Level Manager class that we just built. First, open the engine.h file from the Solutions Explorer window. And then we'll add the declaration for the new function, along with some other new code to the engine.h file. Let's write the code. After hash, include bob.h. Type hash, include double quotes levelmanager.h. In this line, we will include levelmanager.h file. Now, after bob m_bob, add a comment. A class to manage all the levels. Level Manager m_lm. Here, we're adding an instance of Level Manager called m_lm. Next, after bool m_new level required equal to true, add this highlighted code. First, we add a vertex array called m_va level. Then, we add a pointer to an int that will hold the two-dimensional array that is returned from next level. We then add a new texture object for the sprite sheet. After the draw function, write a comment. Load a new level. Void load level. Here, we have added the declaration for the load level function that we will write now. So, right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File, and then in the Name field, type Load Level. Lastly, click Add. We are now ready to code the load level function. Add this highlighted code to the file for the load level function. We start by adding necessary include directives. Inside the load level function, first we set m_playing to false to stop parts of the update function from executing. Next, we loop through all the horizontal arrays within m_array level and delete them. After for loop, we delete m_array level. This line of code calls next level and prepares both the vertex array and m_va level, as well as the two-dimensional m_array level array. The level is set up and ready to go. m_time remaining is initialized by calling getTimeLimit. And Thomas and Bob are spawned using the spawn function along with the value returned from getStartPosition. Lastly, m_new level required is set to false. As we will see in some time, m_new level required being set to true is what causes load level to be called. We only want to run this function once. Great! In this video, we've seen how to code the load level function. In the next video, we'll be updating the game engine. Updating the engine. Previously, we looked at coding the load level function. In this video, we're going to load sprite sheet texture and draw vertex array. To get started, open the engine.cpp file and add a line of code that will load the sprite sheet texture at the end of the engine constructor. After associate the sprite with the texture, write a comment. Load the texture for the background vertex array. Then, m_texture tiles equal to texture holder. Get texture graphics splash tiles _sheet.png. In this line, we're loading the sprite sheet into m_texture tiles. Now, open the update.cpp file. We'll make some changes and additions to this file. After spawn Thomas and Bob comment, we have m_thomas.spawn. We have to comment out this line, and the next line well. And also m_time remaining and m_new level required. Now, first comment load a level. Then write load level function. Actually, you should delete rather than comment out the lines we are no longer using. I've just shown it to you this way so that the changes are clear. All that should be in the if statement is the call to load level. Finally, before we can see the results of the work so far this section, open the draw.cpp file. We'll make some additions to draw the vertex array that represents a level. Now, inside the draw function, after m_window.setView, write a comment, draw the level, and then m_window.draw, m_VA level, and m_texture tiles. Here, we draw the vertex array that represents a level. Now, we have to add the same line again in the split screen view. We do the same for right view. We have drawn the vertex array for all screen options, right, left, full screen. Now you can run the game. Unfortunately, however, Thomas and Bob fall straight through all of our lovingly designed platforms. You can press Enter and see that. For this reason, we can't try and progress through the levels and beat the clock. We'll work on that in some time. This video taught us how to update the game engine. Amazing! In the next video, we'll see collision detection. Hey! This is the last video of this section, collision detection. Previously, we looked at updating the game engine. In this video, we'll be coding the detect collisions function. We will handle collision detection using rectangle intersection and the sfml intersects function. What will be different in this project is that we will abstract the collision detection code into its own function, and Thomas and Bob, as we have already seen, have multiple rectangles, m_head, m_feet, m_left, m_right, that we need to check for collisions. Let's start coding the detect collisions function. To be clear, this function is part of the engine class. Open up the engine.h file and add a declaration for a function called detect collisions. You have to add the declaration. After, void load level function. Write a comment. Run will call all the private functions. Then, bool detect collisions playable character &character. Notice from the signature that the detect collision function takes a polymorphic argument, a player character object. As we know, player character is abstract and can never be instantiated. We do, however, inherit from it with the Thomas and Bob classes. We will be able to pass either m_Thomas or m_Bob to detect collisions. Now, create a .cpp file for detecting collisions. Right-click Source Files in the Solution Explorer and select Add New Item. Then click C++ File and then in the name field type Detect Collisions. Lastly, click Add. We are now ready to code the Detect Collisions function. Add this highlighted code to detect collisions.cpp file. Note that this is just the first part of the function. The first thing that happens is that we declare a boolean called reached goal. This is the value that the detect collisions function returns to the calling code. It is initialized to false. Next, we declare a float rect called detection zone and initialize it with the same rectangle that represents the entire rectangle of the character sprite. Note that we will not actually do intersection tests with this rectangle. After that, we declare another float rect called block. We initialize block as a 50 by 50 rectangle. We will see block in use shortly. Next, we see how we will use detection zone. We initialize 4 int variables, start x, start y, end x, and end y by expanding the area around detection zone a few blocks. In the 4 if statements that follow, we check that it is not possible to try and do collision detection on a tile that does not exist. We achieve this by making sure we never check positions less than 0 or greater than the value returned by getLevelSize.x or .y. Now, all this highlighted code creates an area with which to do collision detection. There is no point doing collision detection on a block that is hundreds or thousands of pixels away from the character. In addition, if we try and do collision detection where an array position doesn't exist, less than 0 or greater than get level size, the game will crash. Next, add this highlighted code which handles the player falling out of the level. For a character to stop falling, it must collide with a platform. Therefore, if the player moves out of the map where there are no platforms, it will continuously fall. This code checks whether the character does not intersect with the float rect level. If it does not, then it has fallen out of the level and the spawn function sends it back to the start. Now, add this highlighted code right after the previous code we added. It's quite large, I must say, but don't worry. We'll go through it and see what it does. This code does 3 things using the same techniques. It loops through all the values contained between start x, end x, and start y, end y. For each pass, it checks some conditions. First, has the character burned or drowned? This line of code determines if the current position being checked is a fire or a water tile. If the character's head intersects with one of these tiles, the player is respawned. We also code an empty if-else block in preparation for adding sound in the next section. Next, has the character touched a regular tile? This line determines if the current position being checked holds a regular tile. If it intersects with any of the rectangles that represent the various body parts of the character, the related function is called stop right, stop left, stop falling, and stop jump. The value that is passed to each of these functions and how the function uses the value to reposition the character is quite nuanced. While it is not necessary to closely examine these values to understand the code, you might like to look at the values passed in and then refer back to the appropriate function of the playable character class in the previous section. This will help you appreciate exactly what is going on. Has the character touched the goal tile? This is determined by this highlighted line of code. All we need to do is set reached goal to true. The update function of the engine class will keep track of whether both characters, Thomas and Bob, have reached the goal simultaneously. We will write this code in update in just a moment. Now, write the last line of code to detect collisions function. Add a comment. All done. Return whether or not a new level might be required. Then write return reached goal. The highlighted line of code returns reached goal so that the calling code can keep track and respond appropriately if both characters reach the goal simultaneously. All we need to do now is call the detect collision function once per character per frame. Open the update.cpp file, and inside m_playing and after update Bob, we have to add a code. Add this highlighted code I've shown. This code calls the detect collision function and checks if both Bob and Thomas have simultaneously reached the goal. If they have, the next level is prepared by setting m_new level required to true. Otherwise, it runs Bob's collisions detection. You can run the game by clicking on Local Windows Debugger button. You can now walk on the platforms. You can reach the goal and start a new level. Also, for the first time, the jump buttons will work. Bob can jump with the up arrow key, and Thomas can jump with the W key. If you reach the goal, the next level will load. If you reach the goal of the last level, then the first level will load with a 10% reduced time limit. Of course, there is no visual feedback for the time or the current level because we haven't built a HUD yet. We will do so in the next section. Let's see some more collision detection. You have to add this highlighted code just after the previous code you added in the update.cpp file within the if m_playing section. This code helps Bob and Thomas jump on each other's heads. You can run the game again by clicking the Local Window Debugger button, and you can stand on the heads of Thomas and Bob to get to the hard-to-reach places that were previously not attainable. You can see how Bob is jumping on the head of Thomas. Also, Thomas can jump on the head of Bob. Awesome! In this video, we have learned collision detection. Cool! That marks the end of this section. We started this section by designing levels in a text file. We then built a level manager class and coded load level function. Then we updated the game engine to use level manager, and lastly, we coded a polymorphic function to handle the collision detection for Bob and Thomas. In the next section, we'll take a look at sound spatialization and HUD. Hi, and welcome to Section 4, Sound Spatialization and HUD. In this section, we will first take a look at what is spatialization and how SFML handles spatialization. We would then move on to building a Sound Manager class and deploying emitters. Later, we'll learn using the Sound Manager class. Lastly, we'd see building a HUD class and using it. Now we move on to the first video of this section, Spatialization and SFML. In this video, we're going to take a look at spatialization and how SFML uses spatialization. Spatialization is the act of making something relative to the space it is a part of or within. In our daily lives, everything in the natural world by default is spatialized. If a motorbike whizzes past from left to right, we will hear the sound grow from faint to loud from one side, and as it passes by, it will become more prominent in the other ear before fading into the distance once more. If we can make our video games a little bit more like the real world, our players can become more immersed. It is probably obvious that the mathematics of spatialization will be complex. How do we calculate how loud a given sound will be in a specific speaker based on the direction the sound is coming from and the distance from the player, the hearer of the sound, to the object that is making the sound, the emitter? Fortunately, SFML does all the complicated stuff for us. All we need to do is get familiar with a few technical terms, and then we can start using SFML to spatialize our sound effects. Let's now take a look at emitters, attenuation, and listeners. We will need to be aware of a few pieces of information in order to give SFML what it needs to do its work. We will need to be aware of where the sound is coming from in our game world. This source of the sound is called an emitter. In a game, the emitter could be a zombie, a vehicle, or in the case of our current project, a fire tile. We already keep track of the position of objects in our game, so giving SFML the emitter location will be quite straightforward. The next factor we need to be aware of is attenuation. Attenuation is the rate at which the wave deteriorates. You could simplify that statement and make it specific to sound by saying that attenuation is how quickly the sound reduces in volume. It isn't technically exact, but it is a good enough description for the purposes of this section. The final factor we need to consider is the listener. When SFML spatializes the sound, where is it spatializing it relative to? In most games, the logical thing to do is use the player character. In our game, we will use Thomas. Moving on to how SFML handles spatialization, SFML has a number of functions that allow us to handle emitters, attenuation, and listeners. Let's take a look at them hypothetically, and then we will write some code to add spatialized sound to our project for real. We can set up a sound effect ready to be played, as we have done so often, as you can see in this highlighted code. We can set the position of the emitter using the setPosition function as shown in the code here. As suggested in the comments, how exactly you obtain the coordinates of the emitter will probably be dependent upon the type of game. As shown here, this would be quite simple in the Zombie Arena project. We will have a few challenges to overcome when we set the position in this project. We can set the attenuation level using the line of code. The actual attenuation level can be a little ambiguous. The effect that you want the player to get might be different from the accurate scientific formula used to reduce the volume over distance based on attenuation. Getting the right attenuation level is usually achieved by experimenting. Generally speaking, the higher the level of attenuation, the quicker the sound level reduces to silence. Also, you might want to set a zone around the emitter where the volume is not attenuated at all. You might do this if the feature isn't appropriate beyond a certain range, or you have a large number of sound sources and don't want to overdo the feature. To do so, we can use the setMinimumDistance function as shown here. With this highlighted line of code, attenuation would not begin to be calculated until the listener is 150 pixels units away from the emitter. Some other useful functions from the SFML library include the setLoop function. This function will tell SFML to keep playing the sound over and over when true is passed in as a parameter, as demonstrated by this line of code. The sound will continue to play until we ended it with this line. From time to time, we will want to know the status of a sound playing or stopped. We can achieve this with the getStatus function as demonstrated in this code. There is just one more aspect of using sound spatialization with SFML that we need to cover. Where is the listener? We can set the position of the listener with this code. This code will make all the sounds play relative to that location. See, this is the code I'm talking about. This is just what we need for the distant roar of a fire tile or incoming zombie, but for regular sound effects such as jumping, this is a problem. We could start handling an emitter for the location of the player. Whenever we want to play a normal sound, we simply call set relative to listener, as I've shown here, and then play the sound in the exact same way we have done so far. Here is how we might play a normal, unspatialized jump sound effect. All we need to do is call listener set position again before we play any spatialized sounds. We now have a wide repertoire of SFML sound functions, and we're ready to make some spatialized noise for real. In this video, we have learned what is spatialization and how SFML handles spatialization. Great! In the next video, we'll see building the Sound Manager class. Welcome to video Building the Sound Manager class and adding it to Game Engine. In the previous video, we got to know about spatialization and SFML. In this video, we're going to take a look at coding SoundManager.h file, coding SoundManager.cpp file, and adding Sound Manager to the game engine. In the previous project, all the sound code took up quite a few lines of code. Now consider that with spatialization, it's going to get longer still. To keep our code manageable, we will code a class to manage the playing of all of our sound effects. In addition, to help us with spatialization, we will add a function to the engine class as well, but we will discuss that when we come to it later in the section. Let's get started by coding and examining the header file. Right-click Header Files in the Solution Explorer and select Add New Item. In the Add New Item window, click Header File, and then in the Name field, type Sound Manager. Finally, click Add. We are now ready to code the header file for the Sound Manager class. Add this highlighted code to the file. There's nothing tricky in the code we just added. There are 5 sound buffer objects and 7 sound objects. 3 of the sound objects will play the same sound buffer, that is M_fire1 sound, M_fire2 sound, and M_fire3 sound. This explains the reason for the different number of sound buffer objects. We do this so that we can have multiple roaring sound effects playing with different spatialized parameters simultaneously. Notice there is the M_next sound variable that will help us keep track of which of these potentially simultaneous sounds we should use next. For now, we have set M_next sound to 1. There is a constructor, Sound Manager, where we will set up all of our sound effects. And these are the 5 functions that will play the sound effects. 4 of these functions simply play normal sound effects, and their code will be really simple. One of the functions, play_fire, will handle the spatialized sound effects and will be a bit more in-depth. Notice the parameters of the play_fire function. It receives a vector 2f, which is the location of the emitter, and a second vector 2f, which is the location of the listener. Moving on to coding the SoundManager.cpp file, we can code the function definitions. The constructor and the play_fire functions will have a fair amount of code, so we'll look at them individually. The other functions would be short and sweet, so we will handle them all at once. So first, right-click Source Files in the Solution Explorer and click Add New Item. In the Add New Item window, click C++ File, and then in the Name field, type Sound Manager. Lastly, click Add. We can now code the .cpp file for the Sound Manager class. First, let's see coding the constructor. Add this code for the include directives and the constructor to the file. You have to add this entire highlighted code. Now, let's go through it. In this code, we load 5 sound files into the 5 sound buffer objects. Next, we associated the 7 sound objects with one of the sound buffer objects. Notice that M_fire1 sound, M_fire2 sound, and M_fire3 sound are all going to be playing from the same sound buffer, M_fire buffer. Next, we set the minimum distance value as 150 and attenuation as 15. Then, we set attenuation for the 3 fire sounds. Next, we set minimum distance for the 3 fire sounds. Finally, for the constructor, we use the set loop function on each of the fire-related sound objects. Now, when we call play, they will play continuously. The values of minimum distance and attenuation were arrived at through experimentation. Once the game is running, I encourage you to experiment with these values by changing them around and seeing rather hearing the difference. Now, coding the play-fire function. Add this highlighted play-fire function. You have to add this entire highlighted code. Let's discuss it. The first thing we do is call listener setPosition and set the location of the listener based on the vector 2f that is passed in as a parameter. Next, the code enters a switch block based on the value of m_next sound. Each of these case statements does the exact same thing, but to m_fire1 sound, or m_fire2 sound, or m_fire3 sound. In each of the case blocks, we set the position of the emitter using the passed-in parameter with the setPosition function. The next part of the code in each case block checks whether the sound is currently stopped, and if it is, plays the sound. We will see quite soon how we arrive at the positions for the emitter and listener that are passed into this function. The final part of the play-fire function increments m_next sound and ensures that it can only be equal to 1, 2, or 3 as required by the switch block. In this if condition, we go back to 1 when the third sound has started. Next, coding the rest of the Sound Manager functions. Add these 4 simple functions. Let's discuss it quickly. The play-fall-in-fire, play-fall-in-water, and play-reach-goal functions do just 2 things. First, they each call set relative to listener, so the sound effect is not spatialized, making the sound effect normal, not directional. And then they call play on the appropriate sound object. That concludes the Sound Manager class. Now we can use it in the Engine class. So open the engine.h file. After hash, include levelmanager.h. Type hash, include double quotes, soundmanager.h. We will also add an instance of the new Sound Manager class. We'll add it after level manager m_lm. Write a comment first. Create a Sound Manager. Sound Manager m_sm. Here we added an instance of the new class. At this point, we could use m_sm to call the various play functions. Unfortunately, there's still a bit more work to be done in order to manage the locations of the emitters, fire tiles. In this video, we have learned building the Sound Manager class and adding it to Game Engine. Awesome! Next up, we'll see populating the sound emitters. Hi, welcome to Populating the Sound Emitters. In the previous video, we learned building the Sound Manager class and adding it to the Game Engine. In this video, we will be coding the populate emitters function. Let's get started then. First, open the engine.h file and add a new prototype for a populate emitters function. After bool detect collision, write a comment. Make a vector of the best places to emit sounds from. Void populate emitters vector 2f ampersand v sound emitters. int double asterisk array level. Next, write another comment. A vector of vector 2f for the fire emitter locations. Then vector 2f m_fire emitters. So here we've added a new prototype for populate emitters function and a new STL vector of vector 2f objects. The populate emitters function takes as a parameter a vector of vector 2f objects as well as a pointer to int, a two-dimensional array. The vector will hold the location of each emitter in a level, and the array is our two-dimensional array which holds the layout of a level. Let's code the populate emitters function. The job of the populate emitters function is to scan through all the elements of array level and decide where to put the emitters. It will store its results in m_fire emitters. Now, right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File and then in the Name field, type Populate Emitters. Lastly, click Add button. Now we can code the new function populate emitters. Add the code in its entirety. We'll study the code and then discuss it. This is the highlighted code. Some of it might appear complex at first glance. Understanding the technique we use to choose where an emitter will make it simpler. In our levels, there are regularly large blocks of fire tiles. In one of the levels I designed, there are more than 30 fire tiles together. This code makes sure that there is only one emitter within a given rectangle. This rectangle is stored in previous emitter and is 300 pixels by 300 pixels. It then sets up a nested for loop that loops through array level looking for fire tiles. When it finds one with the help of this if loop, that is, fire is present, it makes sure that it does not intersect with previous emitter using this highlighted code. Only then does it use the pushback function to add another emitter to V sound emitters. After doing so, it also updates previous emitter to avoid getting large clusters of sound emitters. Great! That's all about populating sound emitters. In this video, we coded the populate emitters function. Let's make some noise now, if you know what I mean. Hi, this video is playing sounds. Previously, we looked at populating the sound emitters. In this video, we're going to add the code for various sounds, that is, jump sound, success sound, fall in fire, and fall in water sounds. To get started, open up the load-level.cpp file, and then we'll add the call to the new populate emitters function. We have to add the call between and repopulate the vertex array as well, and how long is the new time limit block. First, we'll add a comment. Prepare the sound emitters. Then populate emitters m_fire emitters, m_array level. This is the call we've added to populate emitters function. The first sound to add is the jump sound. You'll have to open the input.cpp file. You might remember that the keyboard handling code is in the pure virtual functions within both the Bob and Thomas classes, and that the handle input function returns true when a jump has been successfully initiated. We'll now write the code to play a jump sound when either Thomas or Bob successfully begins a jump. So inside handle input specific to Thomas, block after a play jump sound. Write m_sm.play jump function, and do the same for Bob as well. m_sm.play jump function. Now, open up the update.cpp file and we'll write a single line of code to play a success sound when both Thomas and Bob have simultaneously reached the goal for the current level. We'll write the code after the play the reach goal sound block. m_sm.play reach goal function. Also, within the update.cpp file, I've added some more code. You have to add this highlighted code just after the end if playing comment. Make sure you add it here only. This code loops through the m_fire emitters vector and decides when we need to call the play-fire function of the Sound Manager class. The code is a bit like collision detection for sound. Whenever Thomas stays within a 500 by 500 pixel rectangle surrounding a fire emitter, the play-fire function is called, passing in the coordinates of the emitter and of Thomas. The play-fire function does the rest of the work and sets off a spatialized looping sound effect. Next, open up the detectcollisions.cpp file and find the appropriate place, where we would, and add 2 lines of code. We have to add them after the play a sound comment. Write m_sm dot play fall in fire function. And write a line of code inside the else block, m_sm dot play fall in water function. This line of code triggers the playing of a sound effect when the character falls into a fire tile, and this line will trigger the playing of a sound effect when the character falls into water tile. You can now run the game by clicking on Local Windows Debugger button. You will hear all the sounds, including cool spatialization when near a fire tile. Now, approaching the fire, you'll get to listen cool spatialization. Amazing, isn't it? In this video, we've looked at playing the sounds. Cool! In the next video, we'll take a look at the HUD class. Hey! Welcome to the HUD class. In the last video, we learned how to play various sounds. In this video, we're going to take a look at coding the HUD.h file and HUD.cpp file. The HUD is super simple and not really anything different compared to the other 2 projects we saw in beginning C++ Game Programming Part 1. What we will do that is different is wrap all the code up in a new HUD class. If we declare all the font, text, and other variables as members of this new class, we can then initialize them in the constructor and provide getter functions to all their values. This will keep the engine class clear from loads of declarations and initializations. Let's get started with coding HUD.h. First, we will code the HUD.h file with all the member variables and function declarations. Right-click Header Files in the Solution Explorer and select Add New Item. In the opened window, click Header File, and then in the name field, write HUD. Lastly, click the Add button. We are now ready to code the header file for the HUD class. Add this highlighted code to the file. In this code, first we add one font instance and 3 text instances. The text objects will be used to show a message prompting the user to start, the time remaining, and the current level number. The public functions are more interesting. First, there is the constructor, where most of the code will go. The constructor will initialize the font and text objects, as well as position them on the screen relative to the current screen resolution. The 3 getter functions, getMessage, getLevel, and getTime, will return a text object to the calling code in order to be able to draw them to the screen. The setLevel and setTime functions will be used to update the text shown in m_level text and m_time text respectively. Now, we can code all the definitions for the functions we have just outlined. Next, we'd be coding the HUD.cpp file. As always, right-click Source Files in the Solution Explorer and select Add New Item. In the opened window, click C++ File, and then in the name field, type HUD. Finally, click the Add button. We are now ready to code the .cpp file for the HUD class. Add all this highlighted code. We'll go through it step by step. After we have added the necessary include directives, first we store the horizontal and vertical resolution in a vector2u called resolution. Next, we load the font from the fonts directory that we added back in section 1. This is the font file. Now, getting back to the code. This set of code performs certain operations. The first line sets the font. Second one sets the size. Here, it will set the color, currently white. And last line sets the text of m_start text with the help of setString function. The text is, press enter when ready. The next block of code captures the size of the rectangle that wraps m_start text and then performs a calculation to work out how to position it centrally on the screen with the help of setPosition function. The final 2 blocks of code in the constructor set, the font, the text size, the color, the position, and the actual text for m_time text and m_level text using setString function. We will see in a moment, however, that these 2 text objects will be updatable through 2 setter functions whenever it is required. Now, add this highlighted code immediately after the previous code we just added. In this highlighted code, we are adding getter and setter functions. Let's go through it. The first 3 functions that I just highlighted simply return the appropriate text object, m_start text, m_level text, and m_time text. We will use these functions shortly when drawing the HUD on the screen. The final 2 functions, setLevel and setTime, use the setString functions to update the appropriate text object with the value that will be passed in from the update function of the engine class every 500 frames. That's all about HUD class. In this video, we've looked at coding the HUD.h and HUD.cpp file. Great! With all that done, we can put the HUD class to work in our game engine. So next, we'll learn using the HUD class. Hi! This is the last video of this section, using the HUD class. In the previous video, we looked at coding the HUD.h and HUD.cpp file. In this video, we will add some code to the engine file and the update function, and we'll draw the HUD. To start off, open the engine.h file from the Solution Explorer window. We'll add some code to it. First, we add an include directive for our new class, #include HUD.h. This is the required include directive. Now, we write a code after create a sound manager. Write a comment first, the HUD. Then, HUD space m_HUD. int m_frames since last HUD update equals 0. int m_target frames per HUD update equals 500. First, we declare an instance of the new HUD class, that is m_HUD. Then, we declare and initialize 2 new member variables that will keep track of how often we update the HUD. Next, we need to add some code to the update function of the engine class. So open the update.cpp file and add a code at the end of update function. This is the highlighted code to be added. It updates the HUD once every 500 frames. Let's go through it. In this line, m_frames since last update is incremented each frame. When m_frames since last update exceeds m_target frames per HUD update, execution enters the if block. Inside the if block, we use string stream objects to update our text, that is, SS time and SS level. As you probably expected, however, in this project we are using the HUD class, so we'll call the setTime functions and setLevel functions, passing in the current values that the text objects need to be set to. The final step in the if block is to set m_frames since last update back to 0 so it can start counting toward the next update. Finally, open the draw.cpp file. Now, we'll add few lines of code to draw the HUD each frame. Add this highlighted code inside draw the HUD after m_window set view. In this code, we draw the HUD by using the getter functions from the HUD class, that is, getLevel and getTime function. Notice that the call to draw the message to that prompts the player to start is only used when the game is not currently playing, that is, not m_playing. You can now run the game by clicking on Local Windows Debugger button. Press Enter. See the time tick down. You can also play a few levels. See how time ticks down, level ticks up. Now we're in level 2. I'll play around a bit. See, now we're in level 3, and this is level 4. When a player dies, you have to start from the beginning. And when you get back to level 1 again, notice that you have 10% less time than before. That marks the end of this video. Great! We have learned using the HUD class. Now, to conclude the section, let's recall what we did. In this section, we first looked at what is spatialization and how SFML handles spatialization. We then moved on to building a Sound Manager class and deploying emitters. Later, we learned using the Sound Manager class. Lastly, we saw building a HUD class and using it. Splendid! In the next section, we will be learning extending SFML classes, particle systems, and shaders. Hi, and welcome to the last video of this section, Extending SFML Classes, Particle Systems, and Shaders. In this section, we will start with the SFML drawable class. Then, we would move on to building a particle system, and lastly, we'll see OpenGL shaders and GLSL. Now, we move on to the first video of this section that deals with the SFML drawable class. In this video, we're going to take a look at an alternative to inheriting from drawable and why it is best to inherit from drawable. The drawable class has just one function. It has no variables either. Furthermore, its one and only function is pure virtual. This means that if we inherit from drawable, we must implement its one and only function. The purpose of this is that we can then use our class, which inherits from drawable, as a polymorphic type. Put more simply, anything that SFML allows us to do with a drawable object, we will be able to do with our class that inherits from it. The only requirement is that we must provide a definition for the pure virtual function, draw. Some classes that inherit from drawable already include sprite and vertex array, among others. Whenever we have used sprite or vertex array, we have passed them to draw function of the render window class. The reason that we've been able to draw every object we have drawn in this course is that they have all inherited from drawable. We can inherit from drawable with any object we like as long as we implement the pure virtual draw function. This is also a straightforward process. The header file, spaceship.h, of a hypothetical spaceship class that inherits from drawable would look like this. In this code, we can see the pure virtual draw function and a sprite. Notice there is no way to access the private sprite outside of the class, not even a getSprite function. The spaceship.cpp file would then look something like this. In this code, notice the simple implementation of the draw function. The parameters are beyond the scope of this course. Just note that the target parameter is used to call draw and passes in m_sprite as well as states the other parameter. Now, in the main game loop, we could now treat a spaceship instance as if it were a sprite or any class that inherits from drawable. It is because spaceship is a drawable that we can treat it like a sprite or vertex array, and because we overrode the pure virtual draw function, everything just works as we want it to. Let's look at an alternative way of encapsulating the drawing code into the game object. It is also possible to keep all the drawing functionality within the class that is the object to be drawn by implementing our own function within our class, perhaps like this. This code assumes that m_sprite represents the visual appearance of the current class we are drawing, as it has throughout this and the previous project. Assuming that the instance of the class that contains the draw this object function is called player hero, and further assuming we have an instance of render window called m_window, we could then draw the object from the main game loop with this line of code. In this solution, we pass the render window m_window into the draw this object function as a parameter. The draw this object function then uses the render window to draw the sprite m_sprite. This solution certainly seems simpler than extending drawable. The reason we do things the way suggested, extending drawable, isn't really of any great benefit in its own right for this project. The actual reason we will soon draw a neat explosion using this method is because it is a good technique to learn. With each project we have completed throughout the course, we have learned more about games, C++, and SFML. Possibly the biggest improvements we have made from one game to the next is in the structure of our code, the programming patterns that we have used. Think about the idea for improving our code. Imagine every object in our game is derived from a single, simple, abstract base class. Let's call it GameObject. GameObject would probably have concrete functions for getPosition and others. It would likely have a pure virtual update function because every object updates differently. Furthermore, consider that GameObject inherits from drawable. Now look at this hypothetical code. The code is a big step up in terms of encapsulation, code manageability, and elegance when compared to even this final project. You will notice there are, however, unanswered questions, such as where collision detection fits in, for example. Hopefully, however, you can see that further study, by building lots of games, will be necessary to master C++. Although we will not be implementing an entire game in this manner, we will see how we can design a class, particle system, and pass it directly to m_window.draw m_myParticleSystem instance. Cool, that's about it. In this video, we've learned about the SFML drawable class. Splendid! Next up, we'll see building a particle system. Hi, this is video Building a Particle System. In the previous video, we looked at the SFML drawable class. In this video, we're going to take a look at coding the particle class, coding the particle system class, and using the particle system class. Before we start coding, it will be helpful to see exactly what it is we are trying to achieve. Take a look at this image. This is an image of the particle effect on a plain background. We will use the effect in our game. The first way we achieve the effect is, first, we spawn 1,000 dots, particles, one on top of the other at a chosen pixel position. Then, in each frame of the game, move each of the 1,000 particles outward at a predetermined but random speed and angle. Repeat step 2 for 2 seconds and then make the particles disappear. We will use a vertex array to draw all the dots and the primitive type of point to represent each particle visually. Furthermore, we will inherit from drawable so that our particle system can take care of drawing itself. The particle class will be a simple class that represents just one of the 1,000 particles. Let's start coding. Right-click Header Files in Solution Explorer and select Add New Item. In the Add New Item window, click Header File and rename the file to Particle. Finally, click Add button. We are now ready to code the header file for the particle class. Add this code to the particle.h file. In this code, we have two vector2f objects. One will represent the horizontal and vertical coordinates of the particle, and the other will represent the horizontal and vertical speed. When you have a rate of change, speed, in more than one direction, the combined values also define a direction. This is called velocity, hence the vector 2f is called m_velocity. We also have a number of public functions. First is the constructor. It takes a vector 2f, which will be used to let it know what direction velocity this particle will have. This implies that the system, not the particle itself, will be choosing the velocity. Next is the update function, which takes the time the previous frame has taken. We will use this to move the particle by precisely the correct amount. The final two functions, setPosition and getPosition, are used to move the particle into position and find out its position respectively. All these functions will make complete sense when we code them. Now, moving on to coding the particle.cpp file. First, right-click Source Files in the Solution Explorer and select Add New Item in the opened window. Click C++ File and then in the name field type Particle. Lastly, click Add. We are now ready to code the .cpp file for the particle class. Add this highlighted code to the file. All these functions use concepts we've seen before. The constructor sets up the m_velocity.x and m_velocity.y values using the passed-in vector 2f object, that is, direction. The update function moves the horizontal and vertical positions of the particle by multiplying m_velocity by the elapsed time, dt as seconds. Notice that to achieve this, we simply add the two vector 2f objects together. There is no need to perform calculations for both the x and y members separately. The setPosition function initializes the m_position object with the passed-in values. The getPosition function returns m_position to the calling code. We now have a fully functioning particle class. Next, we will code a particle system class to spawn and control the particles. So, for coding header file for the particle system class, create a .h file as we always do. Just keep in mind the particle system class does most of the work for our particle effects. It is this class that we will create an instance of in the engine class. Name the particle system, so the name would be particlesystem.h. Click on Add once you rename it. Cool! We're now ready to code the header file for the particle system class. Add this code for the particle system class. This is the entire highlighted code. Let's go through this a bit at a time. Firstly, notice that we are inheriting from drawable. This is what will enable us to pass our particle system instance to m_window.draw because particle system is a drawable. There is a vector named m_particles of type particle. This vector will hold each and every instance of particle. Next, we have a vertex array called m_vertices. This will be used to draw all the particles in the form of a whole bunch of point primitives. The m_duration float variable is how long each effect will last. We will initialize it in the constructor function. The Boolean m_is running variable will be used to indicate whether the particle system is currently in use or not. For now, we have set it to false. Next, in the public section, we first have the pure virtual function, draw, that we will soon implement to handle what happens when we pass our instance of particle system to m_window.draw. The init function will prepare the vertex array and the vector. It will also initialize all the particle objects held by the vector with their velocities and initial positions. The update function will loop through each and every particle instance in the vector and call their individual update functions. The running function provides access to the m_is_running variable so that the game engine can query whether or not the particle system is currently in use. Let's code the function definitions to see what goes on inside particle system. So for coding particlesystem.cpp file, right-click Source Files in the Solution Explorer and select Add New Item. In the Add New Item window, click C++ File and then in the Name field, type Particle System. Finally, click the Add button. Great! We're ready to code the .cpp file for the particle system class. We'll split the file into 5 sections to code and discuss it better. Here, I've added the first section of the code. You'll have to add this highlighted code. Let's take a look at it. We've added the necessary includes at the start. Then we have the definition of the init function. We call setPrimitiveType with points as the argument so that m_vertex array knows what types of primitive it will be dealing with. We resize m_vertices with num particles, which was passed to the init function when it was called. The for loop creates random values for speed and angle. It then uses trigonometric functions to convert those values into a vector, which is stored in the vector 2f direction. The last thing that happens in the for loop and the init function is that the vector is passed into the particle constructor. The new particle instance is stored in m_particles using the push_back function. Therefore, a call to init with a value of 1000 would mean we have 1000 instances of particle with random velocity stashed away in m_particles just waiting to blow. Next, add the update function to particlesystem.cpp. I've highlighted the code you need to add. The update function is simpler than it looks at first glance. First of all, m_duration is reduced by the passed-in time dt. This is so we know when the 2 seconds have elapsed. A vector iterator, I, is declared for use with m_particles, and current vertex is set to 0. The for loop goes through each of the particle instances in m_particles. For each and every one it calls its update function and passes in dt. Each particle will update its position. After the particle has updated itself, the appropriate vertex in m_vertices is updated by using the particle's getPosition function. At the end of each pass-through, the for loop current vertex is incremented, ready for the next vertex. After the for loop has completed, the if statement checks whether it's time to switch off the effect. If 2 seconds have elapsed, m_is_running is set to false. Next, add the emitParticles function. This is the code you need to add. This is the function we will call to start the particle system running. So first, we set m_is_running to true and m_duration to 2. We declare an iterator, I, to iterate through all the particle objects in m_particles, and then we do so in a for loop. Inside the for loop, we set each particle in the vertex array to yellow and set each position to start position, which was passed in as a parameter. Remember that each particle starts life in exactly the same position, but they are each assigned a different velocity. Lastly, we increment current vertex. Now, add the pure virtual draw function definition. I'm writing the code you'll need to add. In this code, we simply use target to call draw, passing in m_vertices and states. This is exactly as we discussed when talking about drawable earlier in the section, except we pass in our vertex array, which holds 1000 point primitives instead of the hypothetical spaceship sprite. Finally, we add the running function. The running function is a simple getter function that returns the value of m_is_running. We will see where this is useful to determine the current state of the particle system. To put our particle system to work is straightforward, especially because we inherited from drawable. Open engine.h, add and include directive for particle system.h, and then we'll write particle system object also. After texture holder th, add a comment. Create a particle system m_ps. Next, we initialize the system. Open the engine.cpp file and then we'll write a shortcode, right at the end of the engine constructor. First, write a comment, initialize the particle system, then we'll write m_ps.init1000. So, the vertex array and the vector of particle instances are ready for action. Moving on to updating the particle system in each frame. Open the update.cpp file and we'll write a code for updating the particle system. We'll write this code after the closing curly braces and before the end of update function comment. First, a comment. Update the particles, then if m_ps is running. Inside the block m_ps.update dt as seconds. All that is needed in the code is the call to update. Notice that it is wrapped in a check to make sure the system is currently running. If it isn't running, there is no point updating it. Next, let's see starting the particle system. Open the detectcollisions.cpp file, which has the detect collisions function in it. We left a comment in it when we originally coded it back in section Building Playable Levels and Collision Detection. We'll add a code here after this comment. This is the code to be added. Here, first the code checks if the particle system is already running. If it isn't, checks if the current tile being checked is either a water or a fire tile. If either is the case, it checks whether the character's feet are in contact. When each of these if statements is true, the particle system is started by calling the emit particles function and passing in the location of the center of the character as the coordinates to start the effect. Now for drawing the particle system. First, open the draw.cpp file. We'll write few lines of code in full screen code block as well as right and left code block. After draw Bob, write a comment, draw the particle system, and write if m_ps.running function. Inside the if block, we write m_window.draw m_ps. This is the best bit. See how easy it is to draw the particle system? We pass our instance directly to the m_window.draw function that is m_ps after checking that the particle system is actually running. We add the same code inside the split screen view also. Notice I'm adding the same code to left view, and we have to do that for right view as well. So we have drawn particle system in all left, right, and full screen code blocks. You can now run the game and move one of the character's feet over the edge of a fire tile. You'll notice the particle system burst into life. I'll show you. See? There's our particle system. Awesome! In this video, we have learned building the particle system. Cool! Next, we'll take a look at OpenGL, shaders, and GLSL. Previously, we looked at building a particle system. In this video, we'll learn about programmable pipeline and shaders. We will then code a fragment and a vortex shader. We will also add shaders in our game and load them. Finally, we will update and draw shader in each frame. Open Graphics Library, OpenGL, is a programming library that handles 2D and 3D graphics. OpenGL works on all major desktop operating systems, and there's also a version OpenGL ES that works on mobile devices. OpenGL was originally released in 1992. It has been refined and improved over more than 20 years. Furthermore, graphics cards manufacturers design their hardware to make it work well with OpenGL. The point of telling you this is not for the history lesson, but to explain that it would be a fool's errand to try and improve upon OpenGL and using it in 2D and 3D games on the desktop, especially if you want your game to run on more than just Windows, is the obvious choice. We are already using OpenGL because SFML uses OpenGL. Shaders are programs that run on the GPU itself, so let's find out more about them next. The programmable pipeline and shaders through OpenGL we have access to what is called a programmable pipeline. We can send our graphics off to be drawn each frame with the render window draw function. We can also write code that runs on the GPU, which is capable of manipulating each and every pixel independently after the call to draw. This is a very powerful feature. This extra code that runs on the GPU is called a shader program. We can write code to manipulate the geometry, position of our graphics, in what is called a vertex shader. We can also write code that manipulates the appearance of each and every pixel individually in code called a fragment shader. Although we will not be exploring shaders in any great depth, we will write some shader code using GLSL, and we'll get a glimpse of the possibilities offered. In OpenGL, everything is a point, a line, or a triangle. In addition, we can attach colors and textures to this basic geometry, and we can also combine these elements to make the complex graphics that we see in today's modern games. These are collectively known as primitives. We have access to OpenGL primitives through the SFML primitives and vertex array, as well as the sprite and shape classes we have seen. In addition to primitives, OpenGL uses matrices. Matrices are a method and structure for performing arithmetic. This arithmetic can range from extremely simple high school level calculations to move, translate a coordinate, or it can be quite complex to perform more advanced mathematics, such as converting our game world coordinates into OpenGL screen coordinates that the GPU can use. Fortunately, it is this complexity that SFML handles for us behind the scenes. SFML also allows us to handle OpenGL directly. If you want to find out more about OpenGL, you can get started here. LearnOpenGL.com. If you want to use OpenGL directly alongside SFML, You can read the article at this link. An application can have many shaders. We can then attach different shaders to different game objects to create the desired effects. We will only have one vertex and one fragment shader in this game. We will apply it each frame to the background. However, when you see how to attach a shader to a draw call, it will be plain that it is trivial to add more shaders. We will follow these steps. First of all, we need the code for the shader that will be executed on the GPU. Then, we need to compile that code. Finally, we need to attach the shader to the appropriate draw call in the draw function of our game engine. GLSL is a language in its own right, and it also has its own types, and variables of those types can be declared and utilized. Furthermore, we can interact with the shader program's variables from our C++ code. As we will see, GLSL has some syntax similarities to C++. Coding a fragment shader. Here is the code from the rippleshader.frag file in the shaders folder. You don't need to code this, as it is available in the assets we added back while learning abstraction and code management. The first 4 lines, excluding comments, are the variables that the fragment shader will use. However, they are not ordinary variables. The first type we see is varying. These are variables which are in scope between both shaders. Next, we have the uniform variables. These variables can be manipulated directly from our C++ code. We will see how we do this soon. In addition to the varying and uniform types, each of the variables also has a more conventional type, which defines the actual data. Vec4 is a vector with 4 values. Vec2 is a vector with 2 values. Sampler2D will hold a texture float is just like a float in C++. The code inside the main function is what is actually executed. If you look closely at the code in main, you will see each of the variables in use. Exactly what this code does is beyond the scope of this course. In summary, however, the texture coordinates vtextCoord and the color of the pixels, fragments glFragColor, are manipulated by a number of mathematical functions and operations. Remember that this executes for each and every pixel involved in the draw call on each and every frame of our game. Furthermore, be aware that UTime is passed in as a different value each and every frame. The result, as we will soon see, will be a rippling effect. Now, let's code for a vertical shader. Here is the code from the vertshader.vert file. You don't need to code this, as it was in the assets we added back in abstraction and code management section. First of all, notice the 2 varying variables. These are the very same variables that we manipulated back in the fragment shader. In the main function, the code manipulates the position of each and every vertex. How the code works is beyond the scope of this book, but there is some quite in-depth math going on behind the scenes, and if it interests you, then exploring GLSL will be fascinating. Now we have 2 shaders, 1 fragment and 1 vertex. We can use them in our game. Adding shaders to the engine class. First, you have to open the engine.h file. Add this code, which adds an SFML shader instance called m_rippleshader to the engine class. We will add this instance after texture here. The engine object and all its functions now have access to m_rippleshader. Note that an SFML shader object will be comprised of both shader code files. Open the engine.cpp file and add this code to the constructor. Loading the shaders. Add some code which checks whether the player's GPU can handle shaders. The game will quit if it can't. Next, we will add an else clause that actually loads the shaders if the system can handle them. Now we are nearly ready to see our ripple effect in action. Updating and drawing the shader in each frame. Open the draw.cpp file. As we discussed when we coded the shaders, we will update the UTime variable directly from our C++ code each frame. We do so with the uniform function. Add the highlighted code to update the shader's UTime variable and change the call draw for m_background sprite in each of the possible drawing scenarios. We have to also change the call here. Include the lines of code being written here. It would be best to actually delete the lines of code that I have shown commented out. I just did it this way to make it clear which lines of code are being replaced. Run the game, and you get an eerie kind of molten rock effect. Experience with changing the background image if you want to have some fun. That's it. Our third and final game is done. In this video, we have learned about OpenGL, shaders, and GLSL. In the grand finale, we explored the concepts of particle systems and shaders. Although we looked at probably the simplest possible case for each, we still managed to create a simple explosion and an eerie molten rock effect. This was really a big journey, and hopefully you have a good insight in how to build games in C++. I wish you all the best. Keep gaming.